Okay, it's fine.
Okay, thank you. Good morning. Good morning, everyone. Welcome to this workshop on scalable management of low-code artifacts, which is organized in the context of the Lowcomote project. I am Davide Di Ruscio from the University of L'Aquila, and I'm going to manage this workshop today. Just to give some context about this event. So first of all, this event, as I said, is organized in the context of the Lowcomote project, and the focus of this project is indeed these low-code development platforms. And just to give some context, if we search for low-code development platforms from Wikipedia, what we find is that LSDP are defined as development environments that are used to develop software applications by means of graphical user interfaces and easy configurations instead of traditional hand-coded computer programming. The first use of this term comes from a Forest report in 2014. And in that report, low-code development platforms are defined as platforms that enable the rapid delivery of business applications with the minimum of hand coding and minimal upfront investment in setup, training, and development, of course, of software applications. And so what are then the low-code pushing factors? So why they are getting so popular? And I mean, the reasons around these platforms are getting so, are increasing. There are two main factors, in our opinion. So on one hand, we have the increasing demand for software developers, and there is an European report that do a forecast in terms of demand for software developers, and the demand for 10 million of developers in 2025 is forecasted with an annual increase of 1.7%. This on one hand. On the other hand, there is the shortage of developers in Europe, and this gradually increase, according to the same report, this is going to increase to reach over 600,000 units in 2025. And there is another report from Gartner in 2016 that predicted the market increase for companies developing low-code platforms to over $21 billion over the next 4 years. And just to say that there is this, these are pushing factors on one end, and on the other end we can. Yeah, sorry.
Should we be seeing slides?
No?
Are you sharing slides?
You're sharing your desktop.
And you're saying that only now?
Well, we thought you were just introducing it, like just reading for
I'm sharing slides since the beginning.
We wanted to be nice with you.
Yes, because your presentation is so clear that we didn't need
be shy. And,
yeah, I thought that was a very pretty picture. So maybe that was the thing you wanted to show.
Okay. Thanks, Dimitris.
That's right, no worries.
I just need to understand how to stop to change this. I don't know what happens. It seems that I lost the toolbar, the Zoom toolbar.
You should be able to get it from the top. So at the very top of the screen, there should be something in the middle with options.
Yeah, but it seems that I don't know. I think it seems that I have to close everything. So I will be back in a second.
Okay.
If I manage to close. Seems that everything stopped. Okay, I'm back. Okay, can you see now the slides?
Yes.
Okay.
Yes.
Can you see the slide?
Yes,
Yes.
now we can.
Yes, we
Okay,
can.
good. Yeah, so
Now he's gone.
I can't hear voice. Yeah.
Yes, we lost him.
sorry, I don't know what is going on. Let's try again. Okay. Can you see again the slides, right?
Yes.
Okay.
Yeah.
Then I will move quickly. So just to say that there is an increasing movement and interest about low-code platforms, and for instance, this is a G2 system where you can search for low-code development platforms, and you see that there are many platforms that
I
Did
think we lost him
we
again.
lose David again?
Yes. I think we should renounce to the slide.
Yeah, maybe we should switch to first presentation. No? I don't know if you have enough time.
Shall we move ahead with Ike? Maybe before the break, Davide may say something.
I'd be ready to take over.
Massimo, what do you think?
It's a good idea. Thank you, Ike.
Yeah?
I think so.
Well, I'm a little bit confused. Was I supposed to start at 9?
Yes, indeed.
There was
9:05.
9:05, I think. There was a bit of a presentation from Davide first.
Okay. So, but I have 40 minutes, right? Is that correct?
Yes, 40 minutes.
Okay. Good. Then let me try to share my screen. So is my audio okay?
Yep.
Yeah, that's right.
Perfect. Slide is visible?
Yes, it is.
Yes.
Okay. It's funny, you see this picture here of mine is 20 years old, but there's this nice feature in Zoom that makes me look so young again. I noticed that this morning. So I would like to introduce you to the CDO model repository. That's an open source technology at Eclipse that I started to develop, I think in 2003 at the Eclipse Foundation. So it's pretty old and major, as I think. Over the years, I and my team developed many features that were added to the technology. At the best times, the team consisted of, I think, me plus 14 developers from companies, some individuals. At the current time, there is almost one person in addition to me with occasional contributions, but users contribute from time to time. I think for a technology that is so major and feature-rich, almost feature-complete as CDO, this is a pretty normal thing. So from these many features in CDO, I will demo a few in a few seconds, but two of them are especially probably the reason why I was invited to give this talk, because the combination of lazy loading of single objects plus garbage collection makes models scalable. And we will see, of course, why that is and how it feels. So in contrast to my former talks, I would like to give a demo first. The demo that I'll show will use a comparingly new, a few years old feature called the CDO Explorer, which is kind of a generic user interface for the underlying APIs and partial frameworks within CDO. The CDO Explorer demonstrates the main functions. I have no idea how many percent of the functionality, but there's still a lot of core functionality that is not available in the CDO Explorer. So before I talk too much, I'll switch to a CDO, to an Eclipse workspace. This is the one that I use to develop CDO and maintain it. And what you see here is an example configuration file for a CDO repository server. You can configure network access, so open ports, for example. This will be important for the clients that we use later. And then you can specify multiple repositories and give their properties, storage, mapping strategies, and whatever is needed. Okay, let me start this server. Normally that's very fast. Here on the OSGI console, you could enter CDO and Net4j commands, list the open ports, list the repositories, add users, and so on. But currently that's disabled because there's a bug in the GoGo shell, and that has a bad impact when you shut down the server. It kills wrong threads, so that's currently not possible here. But a fix, I think, is already committed to the Equinox project. So the server is running in the background. So let me start a client, in this case, an Eclipse, deployed together with the CDO Explorer plugins. There we go. So the first thing that's important in the CDO Explorer is the CDO repositories view. Here you would add, similar to the Git repositories or CVS repositories, you would list your CDO repository connections. So there are currently two types implemented. You can connect to an existing remote repository. That's what we'll do in a second. And for test purposes, you can also create a new local repository and connect to it on the fly. That makes it a little bit easier for first-time testers. But we'll use our running repository over TCP. So we call it remote repository. It's on the local host, the port is correct, and it has found it already on the server. it has noticed that authentication is not enabled. So the whole security subsystem is currently not enabled. It knows that branching is supported by the repository. So we can just say, OK, and we have an online connection to this repository. In the context menu, you can disconnect it, then it becomes gray, or a double click just opens it again. So before you can really work with this repository, you have to create a checkout from it. So we picked a name for this thing that is similar to other version control systems. In reality, it does not copy the contents of the repository into the workspace. What it does is it creates a visual appearance that looks like a project in the Eclipse workspace. For the experts among you, this is purely based on the Common Navigator framework. So it's an extension to that. Okay, and as we can see, the repository is empty here. We can give it another label here. I call it my company, because the meta model that we will use to play with this repository is a simple model of a company which purchases and sells products. So the first simple thing we could do here is we create a folder within the repository. Let's just keep the name folder 1. And in that, we create a new model resource. We call it company 1. And when I open it in a generated editor, we see just a sec. So we must create a root object within the resource. So other than EMF's normal generated editor, the CDO editor supports multiple roots. We must pick a class, so a package and a class. And as I said, we'll use this, our company example model. And in that, there's the E-class company. So, and when the label of an object is shown in bold, then that means it's new or dirty. So it needs a commit to be sent to the repository. Saving the editor triggers a commit on the CDO transaction. So I will perhaps use a few terms for things that I will explain later in the slides. So committing and transactions, for example. So now you already see it is in the repository. So let me start a second client with the CDO Explorer so that we can see the collaborative aspects of CDO. In CDO, it's not just a database for models, it also distributes the change deltas that one client commits to the repository to all other clients that want to listen to these changes. And the effect is very easy to show. Excuse me. So before I do that, I have to connect to the same repository here and check it out. And you see the folder is there, my company resource with the company in it. And when I open the editor, I can now show that when I change the name of the company to, let's say, Eclipse, it's first shown as dirty, and when I save it, all the other clients in the network update instantaneously. This can be configured, of course. Some clients might not need that. For example, if you have a client in the network that executes batch jobs or so, you probably don't need these notifications. So there's fine-grained configuration for all these aspects. Yeah, the same thing works in the other direction, of course. So if I create a new customer in this company and save it, it arrives here in a millisecond. I can give it a name and save again. And so teams can collaborate on a model. It's clear and immediately see what the others have done. Of course, collaboration like this can create conflicts, right? So let's try what happens in that case. For example, let's say this client here changes the name to someone and does not commit yet. And this client changes the name to someone else. And the client 1 here commits earlier. Because of these network notifications to the other clients, the conflict is immediately detected before an attempt to commit is even made. We call that fail early transactions. So if I try to do it nevertheless now, the commit I mean, I have basically two options. I can roll back my local transaction, and that means it would go back to the latest server state. So I will not do that now. Instead, I will call merge. And now I can decide. I can see what he has done and what I have done, and I can accept his changes. And now we are on the same level again. Okay. What else can we do here? As you see here, we have a nice history integration. And in contrast, it looks a bit similar to Git, but it is a real-time history. So when I do a change here, let's say I commit a new customer, and this one is called Ike again. You see that the history page also updates immediately. The history, like many things in CDO, are always per whole repository. In the end, you see similar things in Git, right? You cannot switch single projects in a Git repository to different branches. A repository is, especially in CDO, it's a consistent view of the model, or in other terms, it's the history of a model that is consistent reference-wise at any time and in any branch. So what we can do is we can create a new branch in this repository, and that is, for example, done in the repositories view. Let's call it Team A. And again, you see, it appears in all other clients immediately. So remember, this checkout here is still looking at the main branch. The properties show also says that here. I can easily switch it to another branch by moving it and dropping it on the checkout. And now you see that here as a label decoration. Because this branch is not different at this point, the editor hasn't changed yet. But now let's try to add, let's say, a product category called software. And in this category, we call a product Eclipse and a product EF. Save that just to get a few more commits. And by the way, you see that here in the history that we have forked off a branch. Then we have CDO, and I'll save that again. Create a new category, hardware. I don't change all the names now because you got the idea. So, and now you will see that these checkouts really don't copy any data from the repository. They really are just a means to specify where to look in the repository. And by where, I mean at what branch and at what time. So here we see in this other client, we now see the Team A branch. What happens if I switch my checkout to the other branch? You see immediately that everything here has updated on the fly. And that's comparingly cheap. It only depends on the amount of change between the two so-called branch points. In CDO, a branch point is the pair of a branch and a point in time. And that's what a checkout adds in addition to the repository connection. So the three things: a repository connection, a branch, and a point in time, give you a consistent version of the model graph. So there are many ways to impact or change the branch point of a checkout. You can do that via the context menu, for example. You can switch to other branches here. You can do it by drag and drop from here or from here, even in the history. We'll now try to, or actually not try, we'll now look at another nice feature of CDO. If you remember, when we created these checkouts, we used this menu point checkout. There's also an advanced version of it, checkout as. And here you see the default. So there are three types of checkouts. For this type of repository, there are only two available. So both are online and not offline. For offline checkouts, you need a different configuration of the repository. So the difference between the two online types is, one is transactional. That means you can, through this type of checkout, you can modify the model and create new commits in the history. But you cannot switch it back in time. So it always looks at the head of a branch. But there's this other type of checkout, a historical checkout, and that's basically the opposite. This one you can use to switch back the model in time, but you cannot edit it at any point in time because the past cannot be modified anymore. So just let's create a second checkout of the same repository. You see all the branches here. And yeah, let's look at the Team A branch and start with the head of the branch. Oops. Oh, Jesus, I fear that is a bug that someone reported 2 days ago I thought he made something wrong, but it looks, probably should have tested that. Yeah, that's the demo effect. Let me see, what can I do to work around that? No, I fear that's the only way to create these historical checkouts. No. Oh, I must really apologize. So after the meeting, I will quickly turn to the bug that the other user reported. That's a pity, because I wanted to show you that we have, for example, a time machine view where you can use a time slider to switch the model back and forth. Perhaps if I have time left at the end, I can revert to an older version in CDO's Git repository, so that we go before this bug. It must be a comparing a new bug. Okay, so let's demo something else then. So if I switch back this checkout to the main branch, we can do that, for example, by dropping the repository itself on it. And I think you get already the idea, or the fact that switching is really fast, especially if you have been looking at a specific branch point before already, because all the data underneath is cached. So if I want to merge it, so the changes from team A into the main branch, I can also drag the branch and then press the control key modifier before I drop it. And that opens the merge dialog. And again, I could accept, for example, all changes, save them, and now I see that the main branch has identical contents to the team A branch. If you don't believe that, you could compare the two things. So, for example, with a version of this branch, and it tells you there are no differences. Merging and comparing is very fast in CDO, no matter how large the repo is. Actually, that's not true, but the time needed to compare an entire repository between two branch points is proportional more to the meta model than to the actual model instances. Okay, so how much time have I spent so far? So actually, I think my talk ends 5 minutes before 10. Is that correct?
Yeah, but I mean, we lost some time at the beginning, so we can give you some minutes more. So
yeah. Okay. Good. So perhaps I think you got an idea how you can work with CDO. There are many more things to demo, even in the UI, but perhaps I first show you a few slides that explain how CDO can deliver these features, especially, I mean, I'm not sure if you noticed, I didn't close the editor when I changed the branch. And the editor, it's an EMF editor, and it shows e-objects. These e-objects exist in memory, and they were not all removed from memory and populated with new ones. What I want to say is your application, if you build your own user interface on top of CDO, it can keep its references on the e-objects, while CDO is underneath changing the viewpoint, or what we say the branch point, and the model just changes and emits normal EMF notifications. So even the simplest EMF user interface will do what I demonstrated here for you. Okay, we'll keep that in the background in case we have time left after the slides. But let's go back to this. Can you, I think we have seen that already. So you can see the slides again? Good.
Yes.
So the agenda, we saw a small demonstration of CDO. Now I will explain you with the help of slides why EMF alone often is a problem when models become bigger, and what on a low level CDO does against that. And if time is left, I will list a few problems with large models, even with CDO, and what parts of CDO, what features you can use that help a little bit to work with that. So imagine you have a normal EMF application that normally interacts with your model through a resource set. I assume most of you have basic EMF knowledge, right? Okay. So when the application wants to access an object in the model graph, the resource set loads the resource that contains the object and returns the pointer to the requested object to the application. That's what we see here. Notice also that all the objects in the resource have been loaded, not just the one that was requested. From this object on, the application can then navigate over the model, and when it navigates to a model that's in a different resource, the resource set automatically loads that resource and everything starts from scratch. And that's the basic way how models are loaded and navigated. And in a way that's fine, but you see already if the overall model becomes large, the resources are the only means of EMF to do some sort of partial loading of the model. So the boundaries between the resources have to be to some extent be planned while designing the meta model. That's an aspect that is, I would say, not so nice. In many cases, you can live with it, but it's definitely not business model. It's introducing technical aspects at an early stage of the development process. We'll come back to that because in CDO that's different. What's really interesting and not so much known to people is what happens when you want to unload objects with EMF. So that means when the application releases its initial entry pointer to the model. In that case, there are still technical references from the application to the resources. And even within the model, you have at least probably all of these references are hard Java references. And even if you call resource unload, these references will be cleared. The opposite is the case. When you call unload, the single objects all become bigger. That is because in EMF, the only effect of unload is setting the proxy URI of each object. And that is a big string. and a different one for each object. So in summary, you can start with pure EMF, you can start with small amount of memory and then additionally load additional resources, but it's next to impossible to get rid of them unless you release the entire resource set. Okay, in CDO, it's completely different. There's also a resource set, of course, but when the application wants to load a specific object, a resource is created in memory, but only this single object is loaded. And when your application navigates, the needed objects are loaded lazily and on demand, transparently. Even across resource boundaries, you can navigate. And so it often depends on your algorithms. Is the application a user interface for a user? Then it's very hard to predict the navigation patterns, but sometimes you have batch jobs, as I said before. There it's a bit more predictable. In any case, only the objects that are needed are loaded. So now it becomes more interesting. What happens if the application doesn't need these objects anymore? So it throws away its pointer, and with CDO, all these objects that are not needed by anything disappear automatically through Java's garbage collection, including the resources. So how can this work? Sorry, before we come to the details, how this interesting memory behavior is created. Two things. First, I mentioned in the pure EMF application that the resource fragmentation has normally to be considered at modeling time. In CDO, that is true as well, but if you don't want to do that, you saw you don't need to fragment your model at all. You can store 1 billion objects in a single resource because only the ones are needed on demand are loaded that are needed, right? So that is a design advantage or design time advantage that CDO gives to you. So now look at a CDO application, just to get an introduction here. It connects, as we have seen in the demo, to a model repository. Other applications could do that as well. And the general usage pattern is a client modifies objects always in the scope of a CDO transaction. Then it commits the changes, a change set into the repository. And the repository sends invalidation messages to the other clients. These messages can be configured on the core layer. The main difference is they could either just invalidate the objects, or they could already carry the change deltas, which would patch these objects to the new state immediately. So in this case, it was just an invalidation message. So the next time this application here calls a getter or a setter on one of these objects, CDO automatically loads them again. How does that look like in the model repository? So when the application commits 3 objects, the repository, excuse me, the repository stores the first version of these. And when the application modifies them again, the first version is overwritten by the second version. What I want to show here is this is the so-called normal mode of a model repository. It does not store any history. So it's really more like a normal database. But there's a second mode called auditing, where the history is never touched. So new versions of objects do not override the old ones. And as you can see, this adds a second dimension to the object space. Yeah? In this dimension, we have the different objects, and here we have the different versions. The third and last mode of a repository is called branching. And in this mode, you can imagine you have a history of all objects in different branches, which adds the third dimension to the object space. So you can pick the mode depending on your system's need, but not change it after the repository has created with this configuration. So what we saw here, this is really not an object. We said the objects are the things on this dimension. These are really, we call them revisions. And now we look into the inner structure of such a revision. A revision stores basically everything that EMF needs to store in an object, and we see that here on the right side. That is the information in what resource is the object contained, or under what object, through what feature, and these are the actual values that you have modeled in meta model. So the instance data. In addition to that, CDO stores CDO specific information. Of course, the E-class of an object, its own technical ID of the object. This ID can never change between branches or over time. It's the ID of the logical object at any branch point. In addition to that, the branch and the version of this revision in that branch, and 2 timestamps. When was this revision or this version created, and when, at what time was it revised by the next revision? That is everything that is stored. And now let's see how this data is used. So whenever you want to work with CDO, you first have to connect to the repository, of course, and you do that with a CDO session. The session has a network protocol underneath. Depending on the type of protocol, it uses Net4j typically to connect to the server. And the session has a bunch of components that you can work with. The 2 most important components is a lazy package registry that is also connected to the server, and a revision manager. The revision manager is basically a cache for the local revisions and a loader that loads them to the protocol if they are missing. We will just look at one revision now. Or actually, that's wrong, one object with an ID 1. So in CDO, you cannot work with e-objects through the session. You need to open a view. The reason is, from all the revisions that are available per object, one must be chosen. And that's the purpose of a view. All you need to choose a version is a branch point, and that is configured in the view. So this view wires the E object with its revision. There's a second type of view called audit view. What I forgot to say is this type of view always wires the object with the latest revision of a branch. You need an audit view to wire an object with a specific version from an older time in the branch. And these two views are read-only, of course, because potentially they show the past. And when you want to change a model or the object, you need a transaction. A transaction is also a view, but it's not read-only. On the other hand, it can only show you the latest state, but change it for you. So what if you call a setter on this object here? The current version, the latest version, is copied into the transaction. You see it receives a new version already. Then you can change it. And when you commit the transaction, it's sent to the server, the changes. And when the server says, okay, everything is okay, I've stored and accepted it, the new revision is cached and all the views that look at the latest state update to that version. And all clients do that, as we have seen in the demo. So now, how can that happen with E-objects? Normally, E-objects are not scalable. We look at an example here. That is from the library example of EMF. You see the class book, the implementation class of it, has 4 Java fields, generated fields. What is problematic here when we talk about scalability is mostly this last one, because that is a reference to another object. And as I said before, these references cannot simply be cleared. We cannot help the garbage collection. Once a library has been built up in memory, it will stay there until we remove the resource set. So what does CDO against that? It is based on regeneration of the model, and we use a technique to cut out all generated fields from the generated classes. There's a generation pattern called reflective delegation. There's a CDO wizard that can be used to migrate your gen models from legacy style to CDO's native style, and that changes this property. In addition, I mean, now we've removed all the modeled data. It must be somewhere. So in addition, we use the property root extends class to insert a special CDO superclass or base class between E-object and the generated class. That is CDO object impl. And this class, CDO object impl, contains just 3 technical fields. It knows the CDO ID. It has a Java pointer to the revision, but this is not a strong reference. It is a reference that can be garbage collected. And it knows the state of the object, for example, new, dirty, conflict, or clean. And it knows what CDO view has created this object and manages it. Okay, let's have a quick look at the states. I think time is running very quickly now, so I'll go through it very fast. It's similar to Hibernate. I've seen similar diagrams.
Sorry, Heike, sorry to interrupt. We would like also to have a couple of questions from the audience. So if you can,
shall I come to an end?
Yeah, because we are already, we are, beyond ahead with the schedule, and would like to have some questions from the audience. So if you can move quickly to the conclusion so that we can also discuss it.
Okay, so what I can do is I can make my slides available. There's not much missing here now. A pity is that I can't come to the scalable specific topics that I prepared. But again, I will make the slides available. And yeah, if you want to, you can ask me questions now.
Okay, thank you. Thanks, and sorry again for having interrupted you. Thanks for the talk. And first of all, don't ask me to share my slides or my screen because it seems that it doesn't not work. So we have a question from the Felicien. Felicien, if you want, you can ask directly to Eike your question. Felicien?
Hello. This is Felicien. I have one small question from my curiosity. So you mentioned that the lazy loading of object in the research sets different to the main normal loading mechanisms used in EMF. So how does it get done technically in terms of loading that partial part of the resource set? So does the user maybe specify the ID or the name of the specific components you need to use, or I don't get that part.
Yeah, I think I get your question. So there are basically two levels, two technical layers in CDO. The low level, we call it the revision layer. So there are APIs to access any revision of an object by specifying the ID and the branch and the point in time or the version. But that's a low-level thing, and what you get is not an E-object, it's a CDO revision. The higher level is the CDO view or CDO object layer, and there you basically, CDO takes care of loading the right revision, so you are typically not concerned with that. All you have to do is you must configure your resource set with a CDO view or transaction. And in that view or transaction, you specify the branch and the time, the times stamp. And then CDO loads the right revisions for that branch and time combination and gives you a consistent E-object graph.
Okay.
So,
okay,
so from a client perspective, you can work with the model as before. It's only the setup of the resource set that changes.
Okay, thank you.
You're welcome.
Thank you. Thank you, Felicia. Any other questions from the audience?
Yes, I have a question. Yes.
Yes.
Sorry, I would like to know, how do you identify model conflicts and where? So did you identify model conflicts at the level of server side or at the client side?
Interesting question. Thank you. So I think there are two things. It's detection of conflicts and perhaps automatic resolution of conflicts. Yeah, and both things are possible on both sides.
Okay.
So you can detect and resolve conflicts already on the client side. So that is shown on this slide here. So here we have the state machine. So the question is, what happens when you are in conflict state? Normally you would roll back, but you can hook in your custom or default conflict resolvers into a transaction. And that can either interactively or automatically try to resolve conflicts on the client side. That's the traditional mechanism in CDO. But when you then commit your resolve changes, there's still potential that someone else committed earlier. So since a year or so, we also have conflict resolution on the server side. Conflict detection on the server side has always been there, yeah?
Mhm.
Did that answer the question?
Yes, thank you for the answer and thank you for the nice presentation.
You're welcome.
Good. We have, I mean, the last question is from Suru.
Thank you. Thank you for interesting presentation. I have two questions. First one maybe is related to Felician. I want to know that you say when the object is not needed, we will dispose it. I mean, from the memory or repository. I want to ask that how you understand that it's not needed anymore. I mean, there is some analysis, or it's again with time step or something like that.
So interesting question. That's not CDO that detects that. That is Java's own garbage detection and collection mechanism. So for Java developers among you, we use soft and weak references in important places instead of the default hard references that just keep things in memory. You know?
Mm-hmm. Okay, thank you. And another question, I watched your video on YouTube, and you talk about prefetch policies and prefetch and set feature analyzer for this prefetch. Can you just explain a little about these methods, that how they work and how we can set them? Like,
yeah, I'll try to make that short. It's something I wanted to show you before time ran out. So lazy loading, you've seen that lazy loading of single objects is the key to scalability, in my opinion. The drawback is that if you, for example, iterate or traverse a large subtree of the model, and nothing of that is loaded yet. You can do that with a normal EMF program. It looks the same, but it will play a constant ping-pong game with the server, and that makes it very slow.
Allora, prima cosa on va voir sul quel repository vous avez branché. Est-ce que vous pouvez aller sur la...
Massimo?
Oh, moi, c'est même le dernier bouton.
I think that's not for me, right?
No, I don't think so, yeah.
Okay. So you see, with this lazy loading, you can make it scalable, but not necessarily fast. To make it faster, you have to optimize it. And prefetching is one means to do that. And in CDO, there are, I would say, probably 3 or 4 different prefetching mechanisms. The simplest one is this here. You can just call prefetch the next 10 levels under an object. I cannot talk about all of them, but these CDO units are the most modern and fastest way. These units are really stored in the server in contrast to all other things and make it very fast to load them. I think I'll have to leave it at this level of explanation.
Yeah, by the way, I think that you will be happy to get any other questions or comments offline maybe. And it would be great also if you can share with me these slides so that I can share with
I will do that.
The students. Okay.
I would like to say one last word, please.
Yes, please.
So it was a pleasure. Unfortunately, I have a construction place in my home. That's why I have this nice background. and I have workers here, so I can't attend most of the other talks. I will try to chime in during the breaks. And if you have questions, maybe that's an opportunity. Otherwise, I will look through the chat log and I will provide the slides. Okay.
Thank you very much, Ege. Thank you very much for having accepted our invitation.
You're welcome too. Have a nice day and hope that we can talk later. Bye.
Yeah, thank you. Thank you, Ege. Bye. Okay, so let's move to the next presentation. Is from Yuri Di Rocco, that is going to talk about MDEForge. So Yuri, you know that he's from University of L'Aquila, and he's the main maintainer and developer of the MDEForge. So Yuri, can you try to share your screen and start the presentation? I hope that
Yes,
you will
but
get more luck than me.
I think that the previous people should stop the presentation because I can't share my screen.
Yeah, maybe I can. Can you stop your sharing?
Currently, I can stop. I cannot share my screen. Eike, are you there? Can you stop your screen?
I had to reboot Zoom previously.
So, I can fix it.
No, I cannot.
Can you share now? I changed.
Yes, I can share it. Thank you. Okay. Oh,
good. Okay, thank you.
This is the wrong screen. Okay, let me move it.
We see the slides. Huh?
Ah, the slides.
PowerPoint. We see PowerPoint. Yeah.
Okay, perfect. Okay. Can you see my slides?
Yes, perfect. Thank you.
Okay, good. Very good. I am Yuri. I am a postdoctoral researcher at the University of L'Aquila. I am working with Alfonso Pierantoni and Davide Di Ruscion, and today I will talk about MDEForge. So MDEForge is a modeling repository that allows us to apply multi-perspective mining of the collected artifacts. So, as you know, there is an increasing adoption of MD, and this increase provides many tools, languages, models, meta-models, and a lot of artifacts related to MD concepts. So we need a way to store and then to acquire knowledge about this huge amount of data. And for this reason, we think about a model repository that is able to share and then provide some particular feature for modeling artifacts. Okay, so what is the current situation of repository? So we are looking at model repository as a way to store, search, and retrieve artifacts, but not only. So currently, the repository are are doing more than classifying and store and search artifacts. For instance, they are applying the mining techniques for classification. They are applying some search advanced search feature that allow us to customize the search of a specific artifacts. They provide artifacts for simulation or validated artifacts. In a sense, the repository is used for disseminating and also for retrieving knowledge about the data that they are storing. So what we would like to present what happens in other domains. For instance, we would like to see what happens in biology. There is a biomodels database that is a huge repository that consists of 200,000 of models that are models of biological process. Then in another domain, for instance, bioengineering, we have another repository that is called CellML that is based on a CellML language and consists of huge models. They count around 515 mathematical models that are very huge. And then in pharmacology, we have another important repository that is called DDMOR, that share the models, describe the interaction between drugs and patients, and the models are conformed to the PharmML languages. So they have public instances and then provide a way for customizing the model with the organization. And what happens in the context of software? So in the context of software, we have many repositories. Each one has a particular scope and a particular goals. For instance, we can see here that there is Maven Central Repository. Maven Central Repository is a repository that consists of Java archive. We have Eclipse Foundation that counts around 600 projects. We have SourceForge that stores binary sources, and then we have Jenkins for storing the builds of a project. And for instance, also Bugzilla is able to store the data about bugs and so on. And then one of the most famous repositories is GitHub. So by looking at GitHub, we see that in 2018, it reached 100 million of repository, and each repository consists of thousands of files. So there are a huge amount of data that we can use for many purposes. And then we will see what's happened in model repository. In model repository, so as I said at the beginning, we have a very huge kind of artifacts. We have many models, many transformation, many tools around MD stuff. But in the past decade, several model repositories have been introduced, but it seems that no one is attracting contributors for submitting artifacts and other modeling elements. So, for instance, there is RTL Zoo that consists of models and transformation, OCR repository, Grammar Zoo, the free model initiative, and then Remod. So all of them are provided in the last decade, and of course, as we see in the last presentation, we have also a CDO that is a way for storing and collecting modeling artifacts. Okay, so first of all, we would like to understand what are the opportunities that the model repository provides to the users. So first of all, we would like to see that the model repository can enable the generation of user communities that are working on the common purposes. Then the model repository could provide the certified artifacts for verification and validation. So just to have a parallel, there are different different repositories, for instance, a source repository that provide just artifact for the verification and validation. For instance, we can see a JSON repository that consists of models for validating the approach that you are doing. So this is one way that we can, one opportunity we can get by using model repository in model-driven engineering. Then we can have artifacts for learning purposes. We can have traceability between artifacts. The traceability could be between artifacts in the ecosystem, for instance, from model and meta models, for transformations and meta models and models, or traceability between versions. So there are different kinds of traceability. For sure, a model repository can enable tool interoperability by using or relying on services. For instance, we can provide GitHub provides many services for searching, for querying, for cloning, and those services are provided by different kind of access point. For instance, we have in GitHub, we have API, or we have GraphQL, and then many other things in order to enable the tool interoperability between different actors. Then we can also use the data stored in the model repository in order to give some mining aspect. For instance, we can extract, we can classify the artifact, and in particular, we would like to extract knowledge from the data. And finally, the model repositories can enable collaborative modeling when two modelers are working on the same models. So these are the opportunities that a model repository could provide in model-driven engineering. And then we have also analyzed what are the challenges that we have to tackle for implementing a model repository. We identified two kinds of challenges. The first one are technical challenges, and the second one are non-technical challenges. The technical challenges, for instance, we classify it and we tailor the technical challenges among the model repository. For sure, in the model artifact can belong on different kinds. For instance, we have transformation, we have models, we have constraints, we have many kind of artifacts, and a model repository should be able to handle these different kinds of modeling artifacts. Moreover, it should provide advanced query and browse mechanisms that are tailored on the kind of the artifacts. And also a technical changes is the fact that we have to expose the services that the model repository provides as a model services. And for instance, we can run a model transformation, we can store by means of a dedicated services into the model repository, and so on. And also, there are common technical challenges for many repositories that are extension and scalability. So we put the extension as important things in MDEForge, and we will see during the presentation how we have extended the core services of MDEForge for each typical kind of modeling artifact. And finally, there is another technical change that is the federation of repositories. For instance, Modelio provides a way for federating different model repositories and then to query among this federation of repositories. We have also non-technical changes that has the same impact or maybe a bigger impact than the technical changes, because the non-technical changes is not under the control of the developer of a model repository. For instance, we have to incentivize the user to share modeling artifacts. We have a way for licensing the artifact that we are storing on the model repository, and then we have to provide to the user that is uploading a repository guidelines for sharing artifacts and then assess their quality. Not less important, we have to maintain the software repository. This is a very time-prone task that should be done in order to fit the opportunities that we identified in the previous slides. And then I would like to introduce MDEForge. So let me say that this is a mixed presentation. We have few slides about MDEForge, and then we will see by a live demo what we explain during the slide. And then we will back to the slides in order to introduce the next concept. So let me first introduce MDEForge. As I said, it is a community-based repository of modeling artifact. It enables the adoption of model management tools as software as a services. It is modular and extendable, and it supports advanced mechanisms to browse and query the repository. So all those features will be detailed in the next slides. So the main feature of the MDEForge is, of course, the management of artifact that could be aggregated in the workspace and project. In fact, we resembled what Eclipse did by using the same terms. We have workspace that contains workspaces that contain a list of projects that contains a list of artifacts. So this way has been used in order to group modeling artifacts. Both artifacts and project could be private or public. And we can share artifacts and project with other users in a Dropbox-like mechanism. And moreover, we represent artifact inside of mega model representation of those artifacts, where the relation between the artifacts are explicitly stored in the MDEForge. And moreover, during this presentation, we will see few model management services. For instance, we will talk about how to support model transformation, how to browse the artifacts that are stored in the model repository by means of model clustering, and then we will see how to search artifacts. Moreover, we will see how to interact by both web application and REST API. In fact, in the picture in the right side of the slide, there are the very high overview, high abstraction of the system, where there is core components that could be extended inside the MDEForge. And then there are two ways to interact with the MDEForge. One is by using the web access, and the other one is by using the REST API that provides the real services that MDEForge implement. So let me explain a little bit the architecture of MDEForge. This is mandatory because in the next slide, when we are talking about the extension, we will see also how to extend these core services in order to implement the new and advanced services. So if you see here, this picture resembles what we did in the high-level overview of the architecture, where we have REST controllers and web controllers. And then we have core business components. In particular, we have the business components for storing artifacts. We call the CRUD artifact services for storing relations, also for storing project, workspace, and user. And then we have advanced feature in the that will be implemented from the other services, like the search mechanism and the metric providers that is able to calculate the metrics depending on the type of the artifact. So this is the simplest architectural overview of MDEForge. When we are developing MDEForge, we identified three kinds of users. So we have end user, so the user that we would like just play with the web interface or REST API for gathering artifacts. Then we have developers of modeling artifacts. That is a community of users that would like to share the modeling artifact that they implemented on their site. And then we have a more closer to developers, that is a developers of MD extension. So they are experienced users that would like to contribute by proposing new extension to be included in the MDEForge. So first of all, let me introduce how to MDEForge handles relations. So as I said, MDEForge is able to handle different kind of relation by using a kind of mega model representation of the data. So in the picture, we will see that we have a list of meta models that are a list of meta models, a list of models, queries, and transformation. In particular, meta models are conformed to the meta models. Transformation are defined among meta models. It takes as input models or give as output models. And then queries could be evaluated on models, meta models, and transformation. So this is the complexity of the relation that can occur between modeling artifacts and between the modeling artifact that MDEForge supports. So this is the overview of the meta model that we implemented in MDEForge. Here we did some initial choice. For instance, we have workspaces that consist of project. Project can contain artifacts, and user are owner of the project or could share a project. Moreover, user define workspaces. On the artifact, we can define metrics, and we have different kind of metrics. And the artifact could be extended by model, transformation, and meta model. As artifacts are extended by typed artifacts, for instance, model, meta model, and transformation. Also, relation are that came from an artifact and point to another artifact can be the different types. Here we identify the conform to relation that occurs between model and meta models, or the domain conform to relation, the codomain conform to relation that occurs between transformation and meta models. Here, a simple instance of the mega model where we have a demo project where 2 users, in particular Yuri and Alfonso, is working on. The demo project consists of 5 modeling artifacts, 2 models, in particular family model and person models, 2 meta models, family and person, and then a transformation. That is called family to person. In this picture, we can also see that there are different kind of relation that occurs between modeling artifacts. For instance, we have model that is conformed to the core meta model and so on. So this is the core component of the MDEForge. And then we will see an extension of MDEForge. Why we would start with an extension? Because for sure, RTL transformation is one of the key of the success of MDE, because they includes both abstraction and automation. And so MD ATL transformation has been fully integrated in MDEForge. So, I think that ATL transformation is well known during this talk, but ATL transformation are executable models which takes source model and return target models as output. So, as every kind of software program, ATL transformation need to be shared and reused, for sure executed, evaluated, maybe analyzed, and tested. So in this picture, in the right part of the slides, we have a picture, a common picture that resembles how the transformation works. So the transformation is a set of rules that are conformed to the language. In this case, we are talking about ETL transformation, so we have ATL language. The transformation rules are defined among source and target meta models. And then the transformation engine executes the transformation rule by taking it as input source model and produce target models. So this is a simple abstraction of how ETL transformation works. So what we did in MDEForge? For sure, we implemented the possibility to execute a transformation by relying on the relation that occurs between transformation models and meta models. We can calculate specific metrics for the transformation, as for instance, the number of rules, the number of helpers, the number of conditions, and so on. And then we applied 2 advanced features that has been implemented in the MDEForge thanks to the collaboration with the University Autónoma of Madrid, especially with the MISO group. So these 2 features are application of static analysis techniques, and then the automatic testing of the transformation by using generated model. And as other modeling artifacts, MDEForge provides the possibility to organize the transformation in the workspace and project, to store the transformation, and then to share with other users. Here we see how we extract the data model. We extended the data model in order to support model transformation. For instance, we had the 2 relations, typical relations that are domain conformance to relation and domain conformance to relation that occurs between the ETL transformation and then the meta model. And then also we had a specialization of the transformation that is ITL transformation. So, do you remember the overview of the MDEForge, where we have created the artifact, we have the searcher provided, and then here with the blue, the highlighted blue boxes are the elements that is already implemented in MDEForge. The red one are the elements that extend or implement some feature provided by the core services. For instance, here we have ATL transformation services that use the CRUD artifact services in order to support the sharing mechanism, and also they use the possibility to execute, to analyze, statically analyze the transformation or testing it. Moreover, it has 2 important implementation about calculate metrics and create index, because on the create index, then we will see how the search feature of the MDEForge has been implemented. And then we have 2 extensions of the REST controllers and web controllers in order to provide the the ETL transformation as a services. Here, just an overview of what is the result and how we integrate the model transformation. We have 5 parts. The first one is related to the metadata that is common for each modeling artifact stored in MDEForge. The second ones report the possible error when we are that the transformation can have, and the same for the testing service report. And then we have a part for executing the transformation, where is defined what is the input model and what is the input output what is the input meta models and what is the output meta models. For sure, we can then execute the transformation by selecting all the models that are conform to the meta models that are specified here. And then we have a part where we are reporting the metrics of the transformation. We computed among 32 metrics of the ETL transformation. As I said before, we can play with by means of the graphical editor, but also we can play it by with the REST services. And in particular, we also developed a client that automatically interact with the services by providing the information to the user. Let me recap what I did until now by the example. Wait a second, let me open the tool. Can you see the browser?
Yes, we can.
Okay. So this is the MDEForge. We have 3 parts. The first part is browse, search, and use, where in the browse part we stored the public artifacts and project. The search, with the search part, we can search by different methodology artifacts inside the repository, and then the use, where we can upload the artifacts, we can compute metrics, we can analyze the artifact, and so on. So when I'm logging, I logged in the system. So here, the recap of the user. We can have a list of workspaces. For instance, here I have a workspaces that collects KM3 projects. In particular, in particular, I have 2 projects, the KM3 metrics and KM3 2XML. Each project consists of a core meta models, RTL transformation, models. Moreover, as you can see here, I can share the project with the other user. And in this case, I share it with Francesco Basciani. I can go inside the artifacts in order to see what happens. Here we have an artifact that is the meta model for the metrics. We can visualize by textual editor the meta model. And you can see that it is a simple meta model for compute metrics. And then we have different kind of relation that could be shown here. For instance, we have transform through, we can see that these meta models are involved in a transformation that is called KM3 metrics. Moreover, we have also some metrics that has been calculated on these meta models. As you can see, we have 4 meta classes inside the meta model, a number of concrete meta classes 2, and so on. Going back, I would like to show also the transformation. So this is, let me open the same project. Okay, this is the transformation. I have a transformation. We analyze the transformation and we discovered that this simple transformation that consists of less than 300 lines of code has more than 100 errors. And then we have a part for see the metrics. You can see that the metrics here are different for the metric for the meta models, because here we have the number of pathing, the bindings, the number of rules, and so on. And then we have a part that is able to show how the meta transformation are linked to the input and output meta models, and a way for executing the transformation. But we will see later on how to execute the transformation. Okay, now I would like to see how to create a workspace. I can create a workspace. My I create my workspace. I can import a project on my workspace, but in this case, I would not to import any projects. Okay, this is my live workspace. I can create a new project. For instance, let me create a very famous project, family to person. Okay, here I have my family to person. And then I would like to upload some artifact to this project. Let me upload first the MetaModel families. Let me select the file. Okay. Okay, I can add directly to the project that I created and then upload the file. Okay, I uploaded the file, the system automatically computes the metrics and store it inside my workspace. And in particular, in my project. I would also, I would also upload another meta model that is the person. Let me select the meta model. I will add to my project. Okay, it computes the metrics and store it correctly. And then I would like to upload my ITL transformation. So I will upload the families to person transformation. I will select the file. This is a little bit different from the previous upload because it is typically defined on the artifacts. For instance, of course, I can select, but I can parse the file that I'm uploading in order to give important information. For instance, here I see that there is a meta model. This transformation takes just one input meta models, the input models that is conform to the family's meta model, and then there is it generates an output model conform to the person meta models. Here, let me search for the meta model. Okay. Let me. Good, very good. And then I can upload my transformation. Okay, all works fine, and automatically it computes the metrics, it generates this part, and it allows to analyze the transformation. This analyze involves two services that has been implemented in the MDEForge and has been conceived from the MISO group and when I was in visiting in Madrid. I can analyze the transformation, and then we can see that analyzer, the static analyzer of the ETL transformation, identify a possible error. It is a very funny because the family to persons are considered the hello world of ETL transformation, but also the hello world of transformation has a possible error. So if you visualize the error, the transformation, we can see that the error occurs here, and we have a motivation. This is not of the goals of this on this presentation, but it is interesting to see that the hello world program of ETL has an error, a potential error that can be found when we are executing transformation. So here, what we covered how to generate a workspace, how to create a project, how to share the project with other users, and also how to play with the ETL transformation. So let me also upload a model, for instance. I will upload simple model. Let me select a simple model. And then I have to specify the meta model. I specify the meta model in that the models that I'm uploading is conform to. For instance, here we are uploading a simple family. And then I can upload my meta model. Now, if I go to the project and then to the transformation, I can add also the models here. But what I would like to show you is how to execute the transformation. So I can click here, and automatically the input models search for model conform to the meta model that is the meta model, the source meta model of the transformation. Here I have just one model, I can execute it. Okay, the transformation generates the model without any error because I have here there is a log to see the errors. And then we can see the transformation, the output of the transformation. Okay, so imagine that you would like to play with the ETL transformation. You don't have Eclipse, you don't have anything installed. You have to install Eclipse. Then you have to install the plugins for handling the transformation. You have to create the project. You have to import the artifact inside the project, and then you have to to run the transformation by configuring the launcher. So this is take times, and if you would like to improve the speed of your development, you can use MDEForge, but not only by means of the graphical interface, but also by looking at the REST API and the clients that interact with REST API. Let me open by Eclipse, because here there is a simple code that is able to load the transformation and then to load meta models, create a models, and then execute the transformation. So here we have a lot of system out just to print the result of the transformation. But here we have a way for gathering the meta model from the MDEForge part, a way for defining a model that will be uploaded to the MDEForge parts, a way for creating the relation between model and meta model. So as we said, there is a relation between the model that is conform to the meta models. And then we have a way for loading model transformation and analyze for model transformation by statical and dynamic analysis and testing analysis. The statical part is done by an analyzer. The dynamical part is done by testing services that is implemented by Esther Guerra from the MISO group. And then we have a simple way for executing the transformation. So I know that it seems a long code, but mainly they are system out in order to see how the system works. And we can run this code in order to play with the artifact that we already implemented. So here we have simple family, the person, the families, the transformation is called family to person. So, and we will see by running it, hopefully without errors. Okay, is able to load the data and then fetch the system with the result. Here I have the result. Let me open the folder. Here I have the result of the execution of the services. I'm going back to the presentation in order to see more important things of MDEForge. Oh, okay. More importantly, here we also evaluate how many time we spend in order to integrate the analyzer and testing services provided by the MISO group. So we added it by means of Maven because mainly the MDEForge is developed in Spring and it relies on the Maven as a project manager. We changed 6 files. We added only 7 files. And then we integrate both analyzer and testing services in less than 3 days. And we added or changed less than 800 of line of codes. And then we now we would like to see how to search and browsing modeling artifacts. artifacts, because this feature depends on the modeling artifacts that I would like to search.
Yuri, sorry to interrupt. I think that we have about 5 minutes.
Okay. So modeling repository. Okay, we have different kind of modeling repository. We have flat repository, manual classified repository, with or without searching feature. So here, for instance, in the GitHub, we have a plain way to store modeling artifacts, and MFZoo provides a way for classified modeling artifacts, and then we have remote that allow also to search. So what we would like to do, we would like to support the searching of modeling artifacts by means of query mechanism, and that are supported by the indexing part. And for sure, we would also like also to stress the modeling aspect of the MDEForge in order to search artifacts. Here there is how we implement the exception. So essentially, there are each artifact type implements the content extractor that feed the index writer, and then we have a query builder. So we define a different kind of searching artifacts, and here we depict some of them. So for instance, we have the searching operators for the metadata, searching operator that search on typical aspect of modeling artifacts, and then we have the search operator that working on the mega model. So let me do an example here. So let me open again MDEForge. I can search artifacts. Here I can search artifacts from different parts. For instance, I would like to search by using the mega model relations. And for this reason, I can search for any transformation that start from KM3 meta models. And here you can see that we have two transformations, KM3 to matrix and KM3 to XML. For sure, we can also see all the meta models that contains the meta class elements. And by running this query, we can see that there is many meta models that contains a class called element. For sure, we can also join many queries. And for instance, here I have a way for searching all the meta model that contains the element meta classes, and then they are uploaded by the user admin. And for sure, all the artifacts that I store in my repository are uploaded by admin, and I have the same results. I'm going on and very speed because this is a very good feature that we implement on the MDEForge. So we on the MDEForge we applied mining repository. The first mining repository mining operation that we did on the MDEForge is for browsing modeling artifacts. This is done by means of the clustering. So the clustering is a way for grouping similar objects. Here there is an example where we have 4 meta models, in particular MySQL, RelationalDB, my project, and my project, that could be aggregated depending on the different similarity function. There is several clustering methods, and in this approach, we will use hierarchical clustering by relying on the distance matrix. Here, the MDEForge approach is able to calculate the proximity distance that is depicted in the left part of the slides, and then the result is represented by the dendrogram. By cutting at a certain threshold of the dendrogram, we can group together artifacts. Here we see how we implemented it inside the MDEForge by adding 3 extensions: proximity calculator that is able to calculate the distance matrix, the clustering technique that apply the hierarchical cluster agglomerative techniques in order to calculate the cluster, and then a visualizer. Let me do it by an example on the MDEForge. So in MDEForge, I have the public part, and in the public part, I can see the cluster. Okay, so before all that, let me introduce how we define the similarity function. We define 4 similarity functions. 2 of them are based on the structure of the meta models, and in particular, they use the structure of the meta models in order to compute the similarity. Those similarities are calculated by means of MF compare that is able to compute a match model, and then we use this match model to see how to define a similarity function. Then we use also two important similarity functions that are taken from the that we used for the calculated similarity from the text. In particular, we use dz coefficients and cosine similarity. Here, the result of MDEForge of the clusterines the meta model that are stored in the MDEForge. In this particular way, we have 555 meta models that has been classified by means of match-based similarity by choosing a specific threshold. For sure, we evaluated the threshold and the best similarity function for grouping the meta models, and we report this in a paper that has been published in the Kaizen. So here we can see that we have different clusters. Each cluster represents similar meta models. For instance, here the cluster blue represent all the meta models related to the PetriNet. Here I have the meta models that representing state charts. Here we have also state charts grouping together. We have a way for expressing meta models for expressing, for instance, databases, and so on. So this part could be also customized by changing the threshold. For instance, here I'm changing a threshold to 64, I'm applying the match-based similarity, and then the system is able to recompute the cluster and to group differently the meta models according to the thresholds. So the threshold is a way for cutting the dendrogram at specific part. Okay, after that we also used the metric for we used the metric that MDEForge is able to calculate for computing correlation between them. But let me skip to the conclusion. So what we did, we first of all we identified a set of opportunities that the model repository could provide to the MD community. We also identified the technical changes and non-technical changes, and among of these opportunities and changes we design and develop MDEForge. In this talk, we also see how we extended MDEForge to support ETL transformation. We see how we implement specific searching modeling artifacts, and then we see how to browse modeling artifacts by means of the meta models. So this is my presentation. I'm here for any questions.
Thank you, Yuri. I don't know if you have any questions from the audience. Question?
Yeah, I have a question.
Yes.
Oh, this is from the. Hey, hello. So I was wondering, you were talking about meta models. So in the mega model, do you also have something for keeping track of, say, different versions that the meta model goes through, for instance, like relating the different versions?
So this is a good question. Of course, we didn't manage the version of the meta model, but let me open the slides. Okay. Okay. Wait a second. Okay, here, because we have a relation that could be typed and extended by means of other metaclasses, other concept, we can add a new relation that is version relation that links two meta models from a previous version to a new one. Currently, it is not supported on the MDEForge, but I think that this structure could enable the usage of a new specialization of the relation in order to handle also the version of a specific meta model.
Okay, so I was just thinking because, for instance, in GitHub, you have bots that sometimes, they go through your repositories and say, oh, you're using an old version of this dependency, you should update to this one. Here's a merge request for you to, to try and have a look.
Yeah. I got your point. It is a very good point, a very good question, and for sure we would like to implement this kind of. But I think that it is an high impact on the for instance, for searching, because when we are searching, we can look for the last version of the meta model, or we can look on the history of the meta model. So we have to play with it. We have to carefully implement the possible way for versioning meta models.
And I have another question.
Sure.
Then have you tried, say, integrating these with GitHub or GitLab? So for instance, it's quite common that you can give somebody access to your GitHub repository, and whenever somebody pushes a new version, that also pushes things to, like, it would tell MDEForge, and then MDEForge could just pull your models from there. Because in that case, you don't have people that are manually having to upload the XML files or the ATL files and so on.
Yes, we think about that in order to have. So we think at GitHub or a similar modeling, a similar repository in two ways. The first one is for sure in order to demand the versioning to the GitHub. So in this way, we can point directly GitHub and okay, the versioning is done by GitHub, and we can raise our hands. And the second way is to develop some connectors that is able to store artifacts in GitHub. So the persistence layer could be demanded to the GitHub, for instance. And for this reason, we didn't apply it, but for sure we implemented many importers that is able to take files and to take artifacts from GitHub that are specifically conceived for the model-driven artifacts.
Thank you.
You're welcome.
I have a question.
Yes,
okay, thanks. Regarding that model matching, which you showed in the last slide, probably. So, which algorithm did you use for that?
Okay, so in this case, in order to compute similarity matching between, let me open a picture because I think that can explain better than the words. Wait a second. Okay. So in order to compute similarity between meta model, we use two main ways. So the first one is by using textual similarities, and the second one by using structural similarity. For this, for the structural similarity, we use MFCompare, that is a tool able to compute match models between two models or meta models. In this case, we see that there are, in the left part, there is the left one version of the one meta models, and the right part there is another meta model. And MFCompare is able to compute the match between elements belongs to the first meta model to the elements belongs to the second meta model. By using this match model, we are able to compute a similarity function that essentially counts how many elements are in common and normalize these common elements by the size of the meta model that we are considering.
Okay, so I mean, I'm just guessing. So there are different blocks of similar meta models, and like, do you find any way to interconnect those unconnected meta models?
So this part is able to compute similarity between meta models. Then we compute all the similarities in a distance matrix, and we use the distance matrix in order to compute hierarchical cluster. So essentially, what we did here is that.
Okay, thank you.
Okay, so is that we compute this similarity function where row and columns are meta models, and then we produce a dendrogram. By cutting the dendrogram, I can show you the grouping of the meta models.
And like with other groups, there is some meta model matching.
Yes.
With other groups.
Yes.
Okay. Yeah. Okay.
But of course, you can contact Yuri directly
of course.
for more detail. I think that we need to close and have a break because I mean we accumulated some delay because of my fault at the beginning, but also we got. But it's good that we got many questions during the presentation. So I suggest to have a break now, our 10 minutes, and then we'll be back here in I would say at 11:15. Start with the presentation from Antonio. Okay. Thank you.
Thank you, guys.
Thank you.
Thank you.
Thank you.
Antonio?
Hey.
Good. Hi. And can you share your screen so that we can start in time?
Yes. Hold on. Oops. Share screen and share screen. Okay. Can you see it?
Yes. Yes.
Good, good, good.
Just wait a few seconds so that we can start at 11:15 sharp.
Okay.
Okay, I think that we can start is 15.
Yep.
Okay, so thanks, Antonio, for having accepted our invitation to take a part of this workshop. And I mean, I will not spend too much in this introduction. So just to say that Antonio Garcia Dominguez is a lecturer in computer science at Austin University, and today he's going to talk about scalable model query seed with Eclipse Oak, and he's going to talk about say more about what Oak is and his role in Oak. Go, Antonio.
Thank you, Davide. So yes, thank you for the introduction. I think that pretty much sums it up. So I'm going to talk a little bit about this open source project called Eclipse Oak and what is it for and what you can do with it. So let me just go into presentation mode. Right. So first of all, before I start, just want to introduce the whole team in Eclipse Oak. It's not just me. So specifically, Dimitris is here. Hello, Dimitris. He and Kostas were the two people that started the project during the Mondo EU project. There was a work package on scalable querying, and Oak was one of the main deliverables from there. I joined the Mondo project a bit later and then started, contributing to Eclipse Oak. And at some point, I started contributing that much. I basically became the project lead in the Eclipse Oak project. And by the way, I am a committer. I also contribute to the Eclipse Epsilon project that Oak heavily uses. And Dimitris is the project lead for Eclipse Epsilon. So we have these sort of two highly related Eclipse projects happening here. Just before I go on. My next slide is a bit about why Oak exists. I think Ake Steppe already spent a lot of time talking about how trying to put your entire huge model into one single XMI model does not scale. So I won't go too much into it. I'll just talk about the example that I'll be using in this presentation. So there's a case study on extracting models from Java code. It's the Grabat 2019 case study, where they took increasingly large subsets of the Eclipse code base to extract a model from it. And started getting bigger and bigger and bigger. So you see set 1, it's like 27 megabytes, not too bad. Set 2, now you have 270 megabytes, okay. Set 4 is 600 megabytes. I think there's a set 5 somewhere that is on the the gigabytes, and then suddenly the memory usage just skyrockets, right? So then when you have this problem, when you simply cannot just fit the whole model in memory, and you have to you have to wait really long for the model to load, there are two options that you can use. So these options were also sort of discussed by AK in his previous presentation. One is you can break up that model into fragments, just in the same way that you break up a large code base into modules. You can do that with models as well. You break it up into fragments. Of course, you have to design this in advance. But the nice thing with this is that it plays very well with traditional version control systems, right? So if you're using something like Git or Subversion to save, store your models, then it works pretty well with that. But the problem is, if you need to run a query on the whole conceptual model, in the end, you may still have to load all the fragments to answer that query. So then you're sort of back to the original problem that you had. So in that case, Oak is the solution for this scenario, because the idea is that we're going to index each fragment into a NoSQL database. Then we're going to reconnect those fragments, and then we're going to query the database instead of the fragments. Right? So that's one approach. So you could have a very, very large model that is split over thousands of files, And basically, Hog is going to give you that global view by an efficient way. So you're not going to need to have the whole thing in memory if you just want to ask a quick query. The other option, of course, is to just stop using files altogether. And we had a presentation on CDO. CDO's default mapping, because I think that AK didn't have time to talk about it, is a relational database. I think it's an H2 database, if I remember correctly. I do know that recent versions of CDO have support for things like MongoDB, for instance, which is, it's a NoSQL document store. There are other solutions like MDEForge that can, replace the traditional XML-based persistence with graph databases, key value stores, and so on. In our case, Hog is an indexing layer. It's not a storage layer. You're still supposed to use whatever you're using already for storage. And that's kind of the point, because we want Hog to be something that you just add to your solution, and you don't have to re-engineer half of your existing code base because suddenly you have this new need, right? Which is kind of the drawback in a way that something like CDO or MDEForge have, that basically says, okay, you need to re-implement your whole modeling persistence on top of me instead of using whatever you were using, right? We just try to play along nicely with whatever you have at the moment. So the way that Hog is used is, in a normal approach, if you weren't using Hog and you had your fragmented model in a version control system, you will have to check out all the files. So you have to clone your repository or check out your subversion, repository and so on. You have to load those fragments into memory, and you have to run a query. And again, same problem that we mentioned before, you might end up having to load all the fragments anyway. With Hog, the idea is that you tell Hog about, hey, I have this subversion repository, I have this Git repository, I have this folder, or I have this file, or I have this file in some server accessible through HTTP. Please watch over it. And Hog will monitor that location, and it will update itself. It will index the contents of those modules, build up a NoSQL database. Usually, it's going to be a graph database. And if you want to query it, you can just query Hog directly, and Hog will, instead of reloading those model fragments, it will run a query straight on that graph database and give you the result much more quickly. The way in which you use Hog, there are several different ways in which you can use Hog. You can use Hog as an Eclipse plugin, which is what I will be doing in the demo today. But you can also use it as a Java library, and we have experiences, industrial experiences for people doing that. You can use it as a network service. So we have an Apache Thrift-based API that you can use, and there's a number of different serialization options for it. So you can use it through JSON. You can use it through different kinds of binary encodings that are more efficient. For instance, if you want to talk to Hog about things. And we have bindings for that API. We have bindings to that API using Java, using C++, using Python, and using JavaScript, I believe. And we can generate more. It's just the ones that we automatically generate. You can also have it watch at different kinds of locations. So again, we have things like full-on version control systems that expose a history, like Subversion and Git, or just file stores somewhere, like a local folder, local file. They currently open Eclipse workspace or some HTTP location. And we also recently got Docker images as well that we have in case you want to self-host your own Hog server. So also Hog follows a component-based architecture. So Hog is, and this is something that we kind of learned, from working on Epsilon, that it's nice to have a common core that has sort of the main algorithms and the main sort of engine, and then you have all these different extensions, and giving it different capabilities. So the core has the basic algorithms for incrementally updating the graph based on the latest changes to your models. And also it declares a number of interfaces that components must implement. And then we support different kinds of components. So we support different backends. So for instance, you can use Neo4j as the backend. That's the fastest one. For when you have very large models, like you have big monolithic models, that's the fastest one, Neo4j. OpenMBEE is one which supports multi-master mode. So you can distribute the graph over a cluster. It's a bit slower though. GreyCat is one which gives you the ability to index the whole history of the model, and I'll be talking about that later. It does pretty well for heavily fragmented models, but it does not do as well as the Neo4j one. We have like the one big XML file. So depending on kind of the situation, you might want to use a backend or the other. In terms of clients, we have an Eclipse graphical user interface, and we have those 3 web services and their bindings. We also support multiple query engines or query languages. Particularly, well, most of the time you're going to be using the Hawk dialect of the Epsilon object language or the Epsilon pattern language. So it's pretty much your standard EOL with some additions because of certain capabilities that Hawk has. And if you were using the RNDB backend, you could go straight to RNDB as well if you wanted to do that. As for the actual reading of the models, we're not tightly bound to EMF. Your models don't have to be EMF models. In fact, we support Modelio models. So hi, Alexandra, we support Modelio models as well. We support things like Eclipse plugin manifests. We also have, we have some non-official extensions that parse JSON documents, for instance, and turn them into models and index that as well. So it doesn't have to be EMF. Basically, anything that you can write a plugin for, you can treat as a model and index from Hawk. So here's a quick example of the conceptual way that Hawk works. The idea is that suppose you have some library model and you have your library1 XML file that has an author called A1 that wrote the book titled B1. Of course, that model is conforming to a certain meta model. So we have a library meta model with books and authors and so on. And it is that Hawk is going to turn that into this NoSQL graph. And the idea is that an eCore package is going to become a meta model node, an eCore class is going to become a type node, as a physical file is going to become a file node, model elements are going to become element nodes. And on top of that, Hawk will also have its own internal indices for sort of acting as the root or the start point of queries. So it will have an index from the package, ePackage URIs to the meta model nodes. It's going to have an index from the file paths to the file nodes. But also very importantly, you can define your own custom indices by attributes, which is something that, okay, your existing graph databases can already do by themselves, but also by expressions. And that's an interesting thing that, just typical graph databases are not going to do for you. So I'm going to stop here for a moment, and I'm going to do a bit of a demo to show you how to index a very simple Java model and find some singletons. So the idea is I'm going to go to Eclipse. Can you see my Eclipse?
Yes.
Yep, okay. So I'm going to Eclipse. I already have a few, I already have these models indexed in advance in case, we want to run some queries later, but I'm going to do it from scratch. So you see the different steps. So I'm going to be using the Eclipse graphical user interface that Hawk has. So when you install Hawk, you'll get this Hawk view here. And that is the collection of all the different indices that we have. And you can create as many as you want, you can delete them, so on and so on. So I'm going to set up a new index. And the way I do that is I go to this button over here, the add button, and it's going to give me this, this dialog here. Oh, my mouse is to be acting up. I need to enter the name. So I'm going to say, let's see, Lowcomote set1 for the name. The folder where I'm going to keep the graph is going to be Lowcomote set1. Then you want to choose which graph updating algorithm you want to use. There's a time-aware one, there's a regular one. We're going to use a regular one. You can also choose the backend. So again, label DB, GreyCat database, Neo4j, RNDB, or a remote RNDB database. So let's go with Neo4j, for instance. And you can also define a period of time. You can say, I want you to check the different locations every 5 seconds. So these are milliseconds. Every 5 seconds are the minimum. And if you don't find anything, if you don't find any changes, then you can increase the weight to the next check a little bit, up to 512 seconds, for instance, right? If you don't want it to periodically check, I'm going to disable that because it doesn't make sense. I'm not going to be changing the models in this demo. You can just enter 0 for both, and that basically disables it. So you can then just manually trigger updates if you need. Then you'll usually also want to go to the advanced tab, and then you'll want to pick the specific combination of components you want. So again, you have different metamodel resource factories. So these are for loading metamodels. So I just want the EMF1. You also have the different model parsers. Again, I only want to read the EMF models, so that's fine. You can have graph change listeners that basically they're going to react to changes that happen to the graph. So you can have components that react to new classes being added or new model elements being added. You can make it do different things. And as for query engines, we're just going to keep the EOL query engine, for instance. So if I do that and I click on finish, that creates a new index. And this new index is initially empty. So what you need to do is you need to load up some models into it. So the first thing you do is you want to add a meta model. So there's different ways to add meta models. I'm going to say add from workspace, and I'm going to add the Java meta model. So this is going to load up all the packages in that eCore file into the Eclipse index. And now I'm going to tell Hawk, okay, you should be indexing this particular folder or this particular file. So you go to index locations, you tell it to add a location. And again, you have a choice of different locations. You could go with a Git repository, you could go with an HTTP location, a local file, a local folder, some UML predefined libraries. So this is useful if you are indexing UML models, because UML models in Eclipse, they like to use like a predefined set of models in there, and you might want to index them into Hawk as well. Or you could use workspaces, the local Eclipse workspace. And we have actually different ways of detecting changes in Eclipse workspaces because it gets interesting. But anyway, I'll just do local folder and I'll pick the location. So I will go to where I have the models and I pick set1. I'll pick that folder. I'll click on OK. And you'll see now that in the background, it's updating the model and it's loading the file. So particularly, it is loading this file. So you see that it takes some time to load because it's even it's not that big, but even that takes a bit to load. Yeah. So you see that it took some time to open that one. This is just if I open it locally, right? So now what I'm going to do is I'm going to go back to Hawk. So I have this index now. I can now go to any of my queries that I have. So I have a number of queries here. And if I've got this in a repository, and maybe I can share the URL to this later, Davide, in case people want these examples.
Yes.
Yeah. No worries. So this query, for instance, what I'm doing is I'm trying to find the type declaration that has this specific name. So ID input file object. And if I want to run that query, I can, once I have selected this index here, I click on the query button. I say I want to use the query in the currently open editor and run the query, and I get the result. There are all kinds of options that you can provide to a query if you want to limit the scope of the query, like exactly which part of all the models you have indexed you want to use. There are conditions for using paths, using subtrees, limiting by names, providing default namespaces, so on and so on. But we won't go there. There's not enough time for that. So that's one query. And here's another slightly more interesting query where you want to find all the singleton classes in this Java model that you have. So, and we're going to say that a class or a type is a singleton if it has a method that returns an instance of the containing type. So you have a get instance method in class A that returns an instance of A. Then it also has to be public and it has to be static. And you have a query like this. If you want to run that query, you do the same. You click on the query button and you run the query and you get those two singletons. And this is the most basic way to use Hawk when you just want to index some models that you have. The nice thing is, I could go into set1xmi, I could change it, And in this case, I disabled the automatic polling, but I could basically just click on this, and Hawk would immediately check if there were any changes in Z1XMI and update the graph if needed. This is the most basic way to use Hawk. Now, that's fine, but obviously there are some, if your models get large enough, the queries are going to become slower and slower, depending on how you wrote them. So for instance, say we have a query where we wanted to find a type by its name, and we say type declaration, and we want the identifier to be that. Now, if you look at the query, what it really is doing, it has to loop over all the types. It has to follow the name reference, and it has to compare the identifier. And that can be very inefficient if you start getting, you start having a lot of type declarations. So instead, what we can do in Hawk is we can tell it to just index that identifier, the simple name identifier. And then instead of writing the query starting at the type declaration, we can start the query at the simple name. Hawk will notice that you're trying to do a select on something that is indexed, and it will replace that loop with a lookup. And then it will, from there, we'll go straight to the type declaration, right, that contains it. So this is something that you can do. And I will demo it a bit later. I just want to discuss these different options first. Now, let's go back to the query that we had for finding singletons, right? So that was the original query. Again, we have the same problem because, we have to go through all the type declarations. We have to go through all the method declarations. We have to, follow these references and loop over them and check different things and so on. And that can be quite expensive. So what we can do, those three checks that we have, which is if you return an instance of the containing type, if you're public, if you're static, we can tell Hawk to pre-compute these things, and we call those derived attributes because you can extend a regular type with new attributes which are automatically computed from the existing information. The good thing is Hawk also has algorithms for recomputing these in an incremental way whenever something changes. So if you change a little bit of the graph, the impacted part of the graph, if you change a little bit of the model, the affected part of the graph will be updated. So the idea is that you would tell Hawk, look, I want an isPublic derived attribute for method declaration. I want an isStatic derived attribute for method declaration, and I want a isSame return type derived attribute for method declaration. If you do that, and you can do that with Hawk, and I'll show you how to do that in a moment, the query, you could rewrite it like that. And first of all, it's much nicer to read, but also it's going to be faster because you don't have to compute that on the fly, right? That has already been computed for you. So you don't have to follow all those references, try all these different things and loop over things. Now, another interesting thing is that the derived attributes, they are also automatically indexed for you. So, if you look at the improved version of the query that we have, we still have the problem that you have to go through all the type declarations and all the method declarations and then check those derived attributes. But again, because derived attributes are also indexed, we can flip over the query, and instead of going through the type declarations and then through the methods of each type declaration, we can go start with the method declarations, find the ones that seem to belong to singletons, then get the classes from them, get the type declarations from them. If you do that, then the query will look like this. So the query, you'll see that it starts at the method declarations, it goes through all of them, it finds the ones that are essentially your singleton get instance methods, and then from each of those, it's going to get the container of that object, and it's going to give you that as a set. And the container of a method declaration is going to be a type declaration. We know that from the meta model. Now, another thing that you can do is say, okay, fine, but I want to be even faster. I want to be as fast as possible. This is not fast enough. I want even faster. One thing you can do is you can, instead of having this isPublic, isStatic, isSame return type, which are more or less reusable, you can see yourself using them for other things rather than just this one query. You can do something very specific to the query and just basically flag the type declarations that are singletons directly. And if you do that, it will be very, very fast because you just need to go straight to the type declarations that are singletons. So if you do that, and I'll show you how to do that in a moment, then you can just basically write this very silly looking query, which is just find me the ones that are singletons, and it will jump straight to those, because it will have pre-computed this information in advance. So demo time, I'll go back to Eclipse. So the way you do that is I have here the definitions for the different derived attributes. The idea is each of them is basically like a little query. So if I want that is centered around a specific instance of the chosen type. So is public, the way it's written is, okay, something is, a method declaration is public if it has the modifier public. Yeah, and self here is just the method declaration that we're currently deriving attributes for. That's the only thing you have to do. Other than that, it's a perfectly normal PL query. You just get the self, and you have to write the query around that self variable that you get. So you have to tell Hawk about this, and the way you do that is you right-click on the index, you select configure, and then you tell it about different derived attributes. So I'm going to add one. You have to tell it the metamodel URI. Then you have to tell it which type you want to add the derived attribute to. Then you have to pick the name and the type. Then you need to load the EOL source code for it. So I'm doing is public. So there we go. That's the metamodel, that's the type, that's the name, the Boolean, and the source code. We tell it, okay, add that. Now you'll notice that sometimes it doesn't immediately show the derived attribute in this list, and that's because this is done as a background job. So it's not exactly synchronized with the UI, right? The good thing is I can keep adding, for very large models, I can just keep adding derived attributes, and it will be just added to the queue of derived attributes and need to be computed. The bad side of this, side effect of this, is that sometimes you don't immediately see the result here. Now I'm just going to add the other ones. So let me just bear with me for a moment. So method declaration is saying return type, oops, Boolean, and I'm going to do is saying return type. So I add that. Then I will add the other one. So I have my method declaration, and I have my is static. That's a Boolean, and I'm going to do is static, oops, static, and that. And now I'm going to add the last one, which is the type declaration. And that is a singleton, that is Boolean, and a singleton. And that is there. Now you see that if I open the dialog again, I see all four of them. It's just that this little bit of delay because of the way that we use background job straight. So I've got the derived attributes in there. I might as well also add this indexed attribute here. So in order to add an index attribute, and you see this one is just, I'm just basically making it easier to look up things based on the value. So I'll just index the identifier in a simple name. So I'll index the identifier, and I just added that in a moment. And now I can run the queries. So there are different versions of the singletons. This is the original version of the singletons query. And if I run it, you'll see that it runs about this fast. This is not a particularly large model. So I've actually got a bigger model where you're going to notice the difference a bit more. And I'll start it up in a bit, but just so you see how it works. So I get those two singletons. If I use these derived attributes, you see that I simplify the query a bit. So I have is public, is static, and is return type. And I can run the query just fine. And I get the same too. You'll notice at the time, this is not a huge model, this set one, but it went already to 7 milliseconds instead of 13, just by doing that. If I flip around the query and I started the method declarations and then get the e containers from there, then that is going to change things, right? So usually the first time you run a query, it may take a bit longer because it kind of has to warm up the database. But if you run it again, you normally get a more representative time for the query. Then if you just simply go straight to the singletons, right? So you use these singleton derived attributes, you'll run the query and you'll see that the first time it ran, it was 23 milliseconds. Second time runs to 6. This one you don't really notice a lot because it's not a large enough model. But if I go to the set4, I'm going to start up the set4 index in a moment. So that takes a bit because it does have to check for changes first before anything. So okay, so that is ready now to use. So if I try to find the singletons from a fresh, this set4, this is much bigger, right? This is the one that was 700 megabytes, I think. So if I run this query now, you see that it takes a few seconds to run because this one really does have to go through every method declaration and every type declaration. And this can take a while, especially if this is the very first query that you run. So you see that it took 13 seconds, right? If I run the dmethods one, if I run this one, then you'll see that this one it takes only 1 second, so about 2 seconds. If I run this version and I run that, then that will take about 740 milliseconds. If I run the one with when I go straight to the singletons, it's 300 milliseconds. Right? So you see that it does pay off, but especially if you have large models in there. So that's the second demo. Now there's one more thing that you also get in Hawk is that you can have not only derived attributes and index attributes, you can also have derived edges. So for derived edges, I have a toy example, which is a person meta model where you have people and people have parents. So if I just open quickly the model here, it's a very silly example. This is more just to show that we have derived edges rather than about the scale, really, because it's a very small one. So I have some people here. I have John, Jane, Bob, Sally, Robert, Penny, Jack, and Jill. And they have different parents, right? So John Doe, it's one of the parents, one of the sort of roots of the model in a way. Jane Doe, and then Bob Doe is the child of Jane and John. Sally is one of the roots. Robert is one of the roots. Penny is the child of Robert and Sally. Jack is the child of Bob and Penny. And Jill is the child of Bob and Penny. Okay, so you have these sort of two pairs that had kids, and then the kids married and had more kids, right? So if you want to index these in Hawk, I have already done this, so I'm going to take up time doing this. I have already done this, and you can run, you can run just normal queries where, say, for instance, you're just listing all the people in the model, right? I can just run that just fine, right? But if I want to do something like use queries where I use grandparents, siblings, cousins, all that sort of thing, I could start adding more and more references to the meta model, and it will be kind of annoying because all of this is really just something I can compute from the parents reference. I don't need to bother adding all that into the XML file. So what we can do instead is we can define some derived edges. And the way it works is I would add a derived attribute just like normal, but instead of using an expression that gives you a scalar value, I just have an expression that gives you other objects, basically. So I say, for instance, that the grandparents of a person are just the parents of the parents. I have to use flatten here because if I do just parents, I will get a list of lists, and Hawk wants to see a flat list. So I will just flatten that into a single dimensional list. If I want to know the siblings of somebody, then what you'll do is you start from the person, you go to the parents, then you'll use this capability that Hawk has, which is reverse reference navigation, which means I can follow the reference in reverse, right? So now I want to find all the people that have these parents as their parents, which means I want the children, right? When you follow parents in reverse, you're finding the children of those elements. Then I flatten that list, I turn it into a set, and I remove myself. Those are my siblings, right? My siblings are the other children of my parents, essentially. If I add that, and the way you add that is just like I saw before, you can run a query like this, where you can get each person and the grandparents, right? So you get the person, the name of the person, oops, you get the name of the person, and you get the grandparents. So I can run a query just fine, and you get the results as usual. And if I want to find the siblings of Jill, I can just do that as well. And that runs just as well. Right? The nice thing is that we're using the same basic machinery for incrementally updating these things as you change the model. So these are automatically computed for you on the fly, right? Whenever the model changes in an incremental way. So it's quite nice. It's a bit, it's quite convenient. It's quite nice to use. So that's the most basic way of using Hawk. Now, so I went through that demo just now. Now I have, how much time do I have the video?
10 minutes.
Okay, that's really good. So now I have a few sort of greatest hits of other things we'll be doing with Hawk beyond this basic usage, but we just don't have enough time to talk about. So for instance, in 2016, we had an experience integrating Hawk into the SoftTeam Constellation collaboration platform for Modelio models, because they needed to have a way to query models, but not query models in this sort of MDEForge way, where it's at the mega model level, but rather query search models inside from the contents of the models. So they needed that and didn't have that. So what we did was they used Hawk as a library to index the models that were stored in the server, and then you could run queries in EOL over those models. And they didn't have to change their persistence, they didn't have to change anything other than just use Hawk, basically. And then we had a bit of an experiment where we tried from a Modelio project that had a increasingly large sets of models. We tried generating some code, and we found, we measured the time it took the first time after you opened Modelio and the first time after you opened Hawk. And we also measured how long it took for later runs. So runs 2 to 5, we also measured that. So when the models got really large, there was such a difference between the execution time based on Modelio and the execution time based on Hawk that it was even faster with Hawk on the first run, even if you had to pay the cost of indexing, right? So indexing and running the code generation from Hawk was faster than just opening up the project in Modelio and generating the code, even from the very first run. After that, it was faster in Hawk as well, and it was faster in Modelio. But the good thing with Hawk is that you didn't have to pay that initial cost, right? Yeah, actually, you would only pay it once when you created the project, but not once every time you open Modelio. So it was a quite nice speed up, and this works directly with the Modelio model format, right? There's no conversion to EMF happening and anything like that. We also had we have had some extensions to Hawk where we allow people to index the whole history of a model. So we don't keep just the latest version of the model, we keep the whole history of the model. We can do that if you give us a repository that has history. So if you give us a version repository or you give us a Git repository, we can go through all the commits and we can create an index of all the versions of the model. And if you have that, then you can write queries that navigate that history. Because we have some additional extensions to EOL. If you're using the Gregat backend, there are a few more extensions to EOL that you can use. So we have in red, you have some of those extensions. So you have something where you can ask what's the latest version of a type. So types and versions, depending on whenever the set of instances changes, right? They get a new version each type. You can also get the latest version of a model element, for instance. You can also, you see there, there's a line where you can list the versions of an object, and these are the versions of that specific object, right? You can access the previous version, the next version, and so on. If you go to the website of Hawk, we have a section, an entire section on things you can do with it. There's this temporal query section that tells you, okay, this is what you need to do if you want to use this functionality. And these are all the things that you can use if you use these extensions, right? And you can ask different kinds of things. Give me all the versions of this thing, give me the previous one, give me the next one, give me the latest one. Is this always true? Is this never true? Is this eventually true? Is this eventually true this number of times? Blah, blah, blah. Right? Specifically, the example that I'm showing in this slide is because these came from an idea that we could actually use Hawk to follow the evolution of a self-adaptive system that used a runtime model, right? And we're trying to follow how it was working over time. And in this particular example, what we're doing is it uses a form of a reward table to decide which action to pick. So which is the action with the highest reward. And the rewards change over time. And what we wanted to get from this query was a sequence of the minimum change, the maximum change in those rewards, and the average change of those rewards to see if it was stabilizing or if it was like swinging all over the place or something like that. Right? We wanted to see if it was more or less contained. It didn't start like doing wild swings for those reward values. And we were able to write that in a few lines of EOL without too much trouble. We didn't have to write anything too complicated. That's the whole query. That's basically the whole query. And you get those nice metrics on that. Then we also started we kept working on that line of indexing the history of a system. And the developer of that self-adaptive system told us, hey, I want to find out if I have this system making these decisions where sometimes those decisions have short-term losses, but I expect that those hurtful decisions, they end up having long-term benefits, right? And I want to be able to quickly find those cases when I have those short-term losses. So what we tried doing is we indexed with Hawk and the Greycat backend, and we were querying the history, trying to find those short-term hurtful decisions. And one thing we noticed is that, of course, as you have more and more history, the query times were growing as well, right? So what we did is, we said, okay, we already know what we do in these cases. We add a level of indexing for this, so you can replace a loop with a lookup. And we created a new type of divide attribute, which is called a timeline annotation. So the idea is that instead of going through the whole history to find those hurtful decisions, you annotate them. You say, oh, here's a hurtful decision. Here's a decision that looks bad at first glance in the short term. Here's one, here's another one, here's another one, here's another one. We annotate that. We have an index for that. And if you want then to find the interesting versions according to that criteria, you can just use that attribute to directly jump to them. And the results are pretty striking. So you see on the left, we have the times for updating the graph, for querying, running that one query after each time slice of the simulation, without the annotation. And with the timeline annotation, you see that the update times, they don't really change that much, but the query times lower by basically an order of magnitude. So the 99th percentile query time went from 140 milliseconds to 70 milliseconds. It became a lot faster to do this. The latest thing that we have been up to, we have a paper submitted on this that hasn't been published yet, but it has been submitted, is putting a complex event processing engine in front of Hawk to filter the exact moments in time that you want to index. Because we started applying Hawk to follow the evolution of a system that was using reinforcement learning and different algorithms, actually, Q-learning, SASA, deep Q networks. This is something that the machine learning people that we're working with know about. But I know the expert on that. But the idea was that we were getting very large throughputs of events and very large volumes from those reinforcement learning approaches, right? In gigabytes. We started getting throughputs in gigabytes. So we thought, okay, maybe we don't need to store all the history. Maybe we can be a bit selective about exactly which history we want to do. but we want to do it in a very scalable way. So what we did is the reinforcement learning approach. It sends JSON messages to a complex event processing engine that has patterns that select which of those events are interesting. And then the ones that are interesting, it sends off to Hawk, right? This is all happening through MQTT queues. So they are sort of decoupled from each other, right? They don't really, the SEP engine doesn't really know about Hawk, and Hawk doesn't really know about the SEP engine. They just use these message queues in the middle to do everything. And the interesting thing is that we were able to treat an MQTT topic queue as a model repository, and we were able to treat the JSON messages as models. Right? So you see why it's interesting to not be all the time stuck to EMF, because you can do some very interesting things here. And then based on that, we were able to run queries and check certain things about the way that the training went and so on. So those have been the things that we have been up to. If you want to try it out, if you want to know more, there's the link to the project website. Just eclipse.org/Hawk. You can head there. We have, again, we have update sites, we have Java libraries, we have Thrift API bindings to Java, to C++, to JavaScript, to Python. We have Docker images as well, in case you want to use Hawk just from the API. It is an Eclipse incubator project, and the latest stable release is 2.10, which is from November last year. And yeah, we're still working on that project. So far, just a quick summary. If you have a large collection of model files, model fragments potentially connected between them, you can use Hawk to index that and keep up to date a graph database from that you can use to answer queries. You can use index and derived features to speed up queries. And you can index the whole history if you want. You can annotate it with interesting moments in time. You can filter it. You can sample it using the SEP engine. And we have a few things in the roadmap that we're thinking about. So we want to do horizontal scaling. We want to have a web UI. So you don't have to just use Eclipse or the binaries. You can also use it from the web. We want to have more backends. So a newer version of the Neo4j1, MapDB, triple stores, DuckDB, SQLite. We have a few ideas there. We also think about integrating direct support for visualizations through Picto, and adding support for extracting data sets through Pinset. And that's pretty much it. Thank you.
Thank you. Thank you. Thank you, Antonio. Thank you. Any questions from the audience? Any question?
Question?
Yes. Kura, please go ahead.
Yeah, okay. Thank you, Antonio, for a very interesting presentation. So just a small question about query explorer view that you had in Hawk.
Mm-hmm.
So when you compute the results for indexed attributes, the results, they include the time for computation of indices, or indices are computed when you create them? So it's just searching through that index.
So the index is created when you create them. Well, the index is populated when you create it, right? So the time that you have there is just the time. So if I run these, for instance, right, that time is just the time of actually running the query.
Right.
Okay. This is just the query time.
Okay.
Yeah.
Okay. Yeah. And does it support composite indices, or is just the single indices?
Right. So when you say composite, I see being able to, use multiple. So let's see, for instance, right? If you talk about indexed attributes, just the indexing, right? It's normally done through scalar values. But what happens here, for instance, right? When you do this MD is public true and is static, whoops. Oh man, my mouse is doing weird things. So when you do this is public true and is static true and is in return true, Hawk is basically going to get all the instances that meet this condition, all the instances that meet this condition, and then do an intersection.
All right, yeah.
Yeah. One thing that you can do is, if what you're indexing is an integer, a numeric value, Hawk supports ranged queries though. So if you do something like, a number of books greater than 0, Hawk has the ability to go to all the things that have a value greater than 0, right? So it supports range queries. and it supports intersection between different attributes. But if you needed something like a direct composite query, you could approximate it with a derived attribute, because the derived attribute would basically do something like return self something something something, and then concatenate that with something else, right? So you could use a derived attribute to do the concatenation of the multiple things. So you can emulate a composite index by using a derived attribute if you want.
Yeah. Right. Thank you.
Okay, thank you. I think that we need to move on. So thanks, Antonio, again, and I think that you are available for any questions from the students and people attending here. And of course, if you can also share the slides with me so that I can make them available to them. In order to, and thanks again. So in order to the program on the afternoon, I would propose to go ahead with the last presentation from Alessandra. Alessandra?
Hello, hello,
Yeah.
all. Can you hear me? Maybe also see me. Hello.
Hello. So,
I'm not really on the beach, but I'm here. That is northern France. But
just a very short introduction. So we know Alessandra, I mean, from many projects that we have been involved in together. And she's a research scientist in the head of the Modelio research in the software company that currently has been acquired by the DocaPost group, right? So Alessandra, maybe. Okay, so the stage is yours now.
I will tell you something about that. And well, first of all, well, I try to share my slide. Thank you very much to have invited me to this workshop. It has been extremely beautiful to hear how things have been going on with you all, and the things we have done, all of us, during these years, after all the many projects together, Mondo, Meter, CrossMiner. And of course, as you have heard from Antonio, just speaking before me, we had the occasion to work a lot together just after Mondo, because we really managed to reuse OC within one of the soft team ITR project that was called Measure. And that was a really nice experience. I mean, Antonio will share all the paper we wrote, and yeah, it has been very nice, because actually it has been reusing something that was not meant to do that, but it did work fine, and we really had great result. We also manage, we create metrics through OC, and that was not only applied to the metrics we used to do in classes MBA, but also to Archimate models, which was really great. So we managed to go inside the very heart of the language, of Epsilon language, to really talk with OC and to have very, very nice query. We will have soon an open access book chapter where we describe this experience. It was done in the context of another project that is called Data Bio. So we reused it twice, both in Measure, both in this Data Bio. And we hope to use it more in the future. So it's beautiful that we get together on that. So unfortunately, I will not talk about that, which might have been nice. But well, we may have other occasion to explore that. I mean, we never described that to you. So, and we don't want to keep it a secret because it's beautiful to share it. Anyway, so let's go with the talk. I will try to be a bit fast, so we will try to recuperate the time. But so in this talk, I wanted to present. Well, many of you know already all this constellation work that we did, and know Modelio. I will of course introduce it a bit for the one that don't know it, and will introduce a new feature to help scalability that was not there, well, the last time we talked, and actually that is so very new that I had to install it myself when Davide invited me to the talk. But I thought it was worth it, so let's go with the presentation. So things changed also on other levels. not only on the product that I will describe and the evolution of Modelio. It changes also because Softeam has been acquired by the big DocaPost group. DocaPost, as you see, is 6,400 employees, 40 years of history, lot of revenues, many sites in France. I will show you because it's amazing. And lots of clients, and most of all, DocaPost is the numerical branch of La Poste group. So the big La Poste, French La Poste, that of course is on top of that, with even more opportunity and things that can be done. So that is of course a thing that I like, and I'm happy to share with you because it gives us a really lot of opportunity. I am still in the discovering of all of that, but there is really a lot. So a lot of offering, a lot of things that can be entangled with the things we have done through all this year. And so this gave us this nice new perspective. And DocaPost is working a lot in artificial intelligence as well, and touch and trust technologies to help everyday citizen as well, of course, being the numerical branch of La Poste. Softeam is also kind of big and becomes bigger during the last year. Well, the experience here augmented since my last presentation. Also, the employee now are 1,600, and the revenues and the sites we have. In here, I put this nice picture where we have a bit of France geography, but is very nice because you see all the sites that we have with DocaPost. Our headquarters, it changes. It is now in Ivry-sur-Seine, always in Ile-de-France, but not anymore in Paris, but we keep our Paris headquarters. And as for myself, I'm still based in Guyancourt, but we have changed the quarter, we have changed the offices, and so we are now hosted in La Poste building, which is also very nice to see and very big. I have not put picture, but of course I've taken many, and I will share some times on Twitter. So the research area for our group is always software and service engineering, business process automation, system engineering and cyber physical system, and now we had also privacy and GRPD, and the cloud application modeling that has always been there. The standardization efforts are always going on, so UML, CSML, MARTE, and the projects we are involved with are augmented. One recent one started also with Davide and the University of L'Aquila team is AIDO at RT, which is an Excel project, started 1st of April. And then, well, the others, many of them that you know. We keep starting to participate to conference and keeping our research ongoing there, even in this difficult COVID time, which makes it a bit different from previous year. And our open source community is still there, modelio.org, you can check and see what happens there. In here, I will just put on a bit of the current research that we are doing. So AIDO-RT, that's started on 1st of April. It is also about model-driven technology, but linked with artificial intelligence, more semicon cloud application modeling, very DevOps. We are more on security in DevOps, and AIDA, that is a national project that started again in artificial intelligence. So we are trying to help our Modelio tool to grow in this direction. We have a project that is just finalized, another one that we will start, an NR, French, German one that will start in June. So Modelio is growing and always giving its very big importance to standard. Through standard, we also help scalability because, of course, teams can get together and exchange formats and work in a easier and faster way. The tool is quite known. It's open source, but also as a commercial edition with a software as a service version that I wanted to introduce to you during this talk. We have an estimated number of users of 40,000, many downloads, and of course, many years of experience that also started with object tiering. That was the tool before Modelio, but from Softeam and the same team. So what Modelio does, it's used for requirement engineering, system modeling, test modeling, code, test documentation. You can see a few screen in here. traceability and impact analysis, which is very important and helpful also in scalability context. You can see in here some screenshots to give you an idea, and also some of the standard we use like SysML, MART, the structured metric meta model, and the UTP. The current offers, because they changed a bit since last talk, we focused on business architecture, and so the standard are TOGAF, Archimate, UML, BPMN, and our software development, so UML to Java and SQL. But we also investigated more on the scalability part and how to help help organization that needs to manage different teams and that have different needs that may have to be tailored much more often than before. The teams are growing and the number of licenses are changing, and having a solution that is hosted by somebody else, it is more and more interesting from the business perspective. So we want to manage scalability with the Modelio modeling tool offer, and we do that with this new SaaS solution, allowing multiple domains, different team localization, the number of engineers that needs to be there, of course, the size and management of the engineering artifacts that are hosted, interoperability and complexity of the language used, because with standard and standard interchange, we can achieve that. So Modelio facilitates this actor cooperation because stakeholders can collaborate and sharing expertise between each other. We have support for that, so we can define actor roles, expertise, the project, and federate organization. We deal nicely with knowledge management because the knowledge is stored in a coherent, standardized repository that centralized everything, models and documentation. We deal with information sharing at all levels of stakeholder because the information can be shared automatically in web portals. So that allows everyone to have a complete vision of what happens at model level, even if they don't have knowledge, let's say, of particular model elements that are there. And we can have a vision of everything in the model. We manage the requirement and also have this impact analysis that let us go directly on the touchy place of the models where we may need to work and where we may have problem. That was particularly the case with the COVID situation, because actually we are modeling enterprise architecture, and it was very important to be able to follow up customer to tell them where the problem may be in their enterprise architecture, and they can be faster to solve them. And especially, we have also have a nice white paper on the server on that, how we can help the organization to have some transition and to adapt to the new context, like the teleworking and new way to access resources and new approaches. And that thanks to the enterprise architecture that were modeled before, and that could be adapted much more easily. And we are, of course, interested in pursuing in this direction because, of course, that is something that is very much needed because the organization need to recover faster and with situations that can arise as that has happened to all of us with the COVID. So we are also using this scalability capability in the running projects. We usually have collaborative specification and requirement management. We will do that soon in AIDO, that is AIDO 30 that is going to start. We are responsible for the collaborative specification and requirement management. And of course, we will use Modelio for that. But we use that also in other contexts, like, for example, the Morphemic project, where we are responsible for the profile for cloud application modeling and execution language. We can manage to have feedback from all the partners on what is happening in our models, and we can share and collaborate with that. And with Marjorie, you have heard Antonio already, we also had the modelization of all the metrics with the structural metric meta models that was done collaboratively by all partners sharing the same repository. And with DataBio, we managed to model with Modelio 30 pilots and to have the architecture, enterprise architecture of all of them modeled. And well, for CPS Worm also we had collaborative creation for attack trees, where in there we were linking these security models to the CPS models, which was very nice, interesting, even if not standardized and not UML, but Modelio managed very nicely also that. So we have a brand new module to model attack trees. If you are interested for that, it is in our research GitHub space. I will send you the link. And also for AIDA, I will show you the domain because it is interesting and nice, and we can use this technology for our project to help the collaborative work within the teams. And you see, as I said, the scalability through the collaboration support for all the stakeholders is actually our main advantage, and it really makes life easier in many contexts. And one of them, European project, where usually we have many different partners with many different backgrounds and with many different components. So as I said, we can have everything on the web, so everyone, even not expert, can check out what we do in the models. And then analyst, architect, or DPO, data processor, or in the organization now, it's very important. They can use the Modelio editor. They can import and export document. They can use the client as administrator. I will show you that, because of course the software as a service Modelio can be managed by administrator. And in here we can build profiles like with Modelio Studio. And in here you see plus and minus to say the experience in modeling that is needed to do all of that. But the nice thing is that everything goes with a single Modelio repository, which of course help us a lot, because in the real context of real running organization, we really see these different kind of expertise and needs from these different stakeholders. So also the scalability is managed through the consistent sharing of documentation. So we have this consistency control, we can edit assistant and the graphical capability. The document generation is, as I said, the repository shared with stakeholders. And now I come to this new Modelio offer that leads us to a new ground of things. That is a brand new idea, but I don't think it's in the market, but maybe now things are moving. But actually we are hosting the models of also other organizations on our server. So that allows to have the software at your disposal. It adapts to the load increase and decrease of projects and teams. And the person using this solution don't have to worry about the material administration of the tool, how the server is, how the space they need, for example. That is all given to somebody else that deals with the solution. In this case, to the Modelio Softeam team. And of course, the solution is accessible to team regardless to the location, and the server manager can organize the collaboration of teams and a repository. You see in here one of the new pages of the offer. It's the teams can be as little as up to 4 users, so standard, or more than them. And of course, it is always available, the solution. There is the support, and you can monitoring the solution. And the new idea is that it can be hosted somewhere else, and having the modeling tool as you know it. And team can access these tool and models. We can have synergy as before, but this permanent support at both material and functional level. And the license, of course, can be adjusted. The simple administration, of course, you will see a bit. I will show you something if we have time, but I put some screenshots so you will have it. And we can have this not expert user always on the web. So in here you see some screenshot. This is our research sandbox where I can play, let's say. And so in here you see that we can log in this Modelio software as a service. You can see my playground projects, and you can see the management of the project, how they are. I can create new project. I can define the team members of this project. I can also import an existing project in Modelio server, and I can basically manage through this interface everything related to the usage of my organization, and in this case, of course, to my RD sandbox domain. So in here you see that I can decide to open this Modelio SaaS client and open a specific project in my sandbox. Those projects are hosted on Modelio server, so they are not anymore on my drive. And I have not worried about the server resources and management. And of course, I have not to worry if my team grows, if I need more license. For example, for the coming AIDO project, I have already, well, of course, that it is not open source, but for the project it is available. I have already prepared for like 40 licenses to be shared. And if we need more license, I will manage to have more license, and that will be very easy to manage, and that will help scalability, especially for the manager of these kind of things. And you see that in the context of European project, but you can imagine with big organization, that is really interesting. And the manager can check and how things are going on a nice dashboard. So the CPU that is used, the memory that is used, the disk that is used, and the users that are there. You see in there that our R&D team, you know, many of them, some of them are there. And but of course, there can be many more, like even in European project, you have in AIDO 36 partner. Let's imagine that at least one partner will have access, maybe 2, 3. I mean, it starts to be bigger even in our European project context. And so you can create project, you have different possibility, and you can configure this project. So you can define who are the members in the project, you can define who are the administrator, and of course you can remove members if they are not interested anymore in your project, or if they have left the company or the project. That happens as well. And you can have multiple domains. So I showed you before the sandbox that we have for the RD project. In here, there is the specific domain for a specific project. That is our AIDA project, the French one. So you see some French word maybe in the description. And we can create a domain for each one of our RD projects. And of course, for each one of the projects that one organization needs. So in here, you see an example of this project. We can open it and we can go to this particular model. You see in here a requirement diagram, but just to show you that you can go inside the specific project. In here, you can also open 2 different clients at the same time. Of course, my machine is already with 2, but you can also do more than 2. It depends, of course, that is on the client side. But in this case, you see that I am working in parallel with 2 different domains, the sandbox that I showed, and this AIDA project environment that we have. So I will have a little demo if we have time to show you live what that looks like. But let's say that the advantages of course the central repository, the collaborative work focus. I will show a little example of how we do that. Multi-standard with format exchange, the SaaS solution. We have multi-stakeholder management. A solution that is open extensible, that I didn't go too much into that, but we can add many different profiles to Modelio and many different contexts, and that business process orientation. I have left in here all the links, of course, modelio.org that you know, and this is a solution that is not open source, but that we are using in projects since it's very convenient to help scalability, let's say, because we are many and with different needs. So I will send that I will give them to Davide, of course, and I will now show just a little example. I will try to be fast if I manage to go in here. So here is the agenda. In here, you see the Modelio server. So in here, from here, I can go to the project. So for example, this paillasson, that means like a carpet in French. That is really a toy example, but we can see that. We can see when it has been created. I created like in 2021, and we can say that we see the work models that are in there, the modules, and we can see we have Archimate, for example. We can see the users that are allowed to see this toy example, and they should appear. And we can add members, of course. They will be added to that, and we can define members as administrator of the project, and we can of course remove members. So let's now go, for example, to this model. We can open Modelio server. I have it already open, but just to maybe we can I'll try to close it and reopen so you will see it better. Okay, so in here I can open this Modelio server client. I don't know why it's right here. And we can see from the client perspective what's going on. So in here you see, you are still seeing my screen, right?
Yes, yes.
Okay, so in here you can see the server side of things. What happens on the server side? The server can also be monitored, but now we really want to go to the client side. So in here you see the splash screen of Modelio. We can decide the domain where we want to go. So in this case, my user want to go to the Modelio sandbox, a research sandbox. So I will log in to this Modelio source, opening it. So we have to wait that it opens. I hope that it does not disappear. So I try to open it again. Somehow I lost the screen. Yeah.
We see the projects with the screen with the 4 projects, no?
Yeah, that is still the server. The client is going to be open. I unfortunately had the idea to close it, and I had 2 open actually, so but I hear it appearing, so sorry, it was on the other screen. In here you see our client. So in the client, the user, so you see in here the server behind, and in front of it we have the client, and you see the project that are associated to my user, to me. And so, for example, we can go to this playground, so I don't do anything wrong to the rest of the team with my test. So I'm opening this carpet example scenario. Actually, it is a company that builds carpets, and there are many different carpets, and they are with many different material that is in the context of enterprise architecture. And so we are using the Archimate standards in here, which we used a lot in the last period for enterprise architecture, and it is one of the main building block of Modelio business architect solution. And in here you see well the various important parts that are in Archimate, like the requirement, the business rule, the goal, the KPI, the risk, the various tests. But what I wanted to show is the collaborative environment. So what it is called travail de groupe, and in here it is in French, but you can see in them the same opportunity and feature that SVN has. So for example, prendre le verrou is lock the model. So I'm locking in this very moment. So all the other teams member won't be able to access these elements, and I can perform some work on it, and I can add things. I can add another carpet that is done maybe in here. It's multicolor and many other elements. But the important thing is that at a certain point I can commit to the rest of the team the work that I've been done, so that everyone is on the same line with this particular element. And that proves to be very helpful. And you can imagine with also big projects, not only big companies, but it is absolutely important to manage this kind of work. So I think I'm done. I don't know if you have any question. I will show, of course. Well, you have my contact detail. I will give the slide to Davide,
Yes.
and you have all the links in here.
Thanks, Alessandra. Thanks, Alessandra, for the presentation. And I don't know if there are questions from the audience. Yeah, I mean, I think that you show different. You show scalability, let's say, from an organizational point of view, in the sense that where we have different people of the team, I mean, big teams, and thanks for that. And concerning and also you show how to collaboratively develop models, and by using maybe a different way of I don't know, collaboratively working on the same model, because this modeling, for instance, in CDO, I guess the technology that is behind is a little bit different, because you are using a kind of SVM-like approach, no? Because you have first log the elements, for instance. So, but it has been very good, great to see also these other possibilities provided by Modelio. Any other questions before we close? Question? Okay, I think that there are no other questions. So thanks again, Alessandra. So please share with me the slides, and I would close this session now. And now, I mean, we are going to have a shorter lunch break. That has been good because we had lots of discussions and good presentations. And I would close now, and let's see you at 1:30. Okay, almost 1 hour. Thanks, Alessandra.
Thank you. Ciao.
Ciao, ciao.
Ciao.
Thank you.
You're 1:30.
Thank you, Alessandra.
Ciao.
Hello, Agos.
Hello, Davide.
Hi. Shall we try the screen sharing? Can you try with sharing your screen so that we can start?
Yes. What I would like to see, how does it work with... yeah. I don't know if I check because now I have the double monitors and last time I haven't checked that. Let's see. I will share screen 1. So it will be a full screen share. And if I say, we should see the presentation mode,
yes,
right?
Yes, perfect.
Very nice.
Okay, you can keep this.
Okay. Okay. So as I mentioned, I know everybody was listening, but it's important to mention that my presentation is more on the, but what I have seen from Eike, he was also focusing on the examples, let's say, to exemplify how CDO works. If somebody was able to follow his workshop, I think that particular guy, is really well versed in AMF, EMF, and the other things because it was quite content heavy, I would say, the presentation itself. Okay, this is what it is. Good. As I mentioned, I'm not planning to have an online demo, so it's more like how it works under the hood. What can it do? What do we mean about that? And if somebody then is, required to work, can check the demo, can check the examples we have, that is documentation and everything. So that's the main idea here.
Okay. Yeah, I think that we can start in order to avoid accumulating delays. So let's start sharp. So welcome back to this afternoon session. That is going to be busy as well. The first presentation, the first talk is from Agos Horvath, and Agos is CTO from the IncQuery Labs. He's very experienced in model management tools, model transformations, and what he's going to present today is details and things about VIATRA and reactive model processing. So, Agos, the stage is yours.
Thank you. So, hello, my name is Agos Horvath, and thank you for the nice introduction, Davide. Currently, I'm a CTO in IncQuery Labs. I don't know where that particular text field disappeared from my presentation because I had it 2 minutes ago, but no problem with that. And today we are going to talk a little bit about reactive model processing and how it is done within the VIATRA framework, and how, let's say, we have moved forward into something called the IncQuery Model Analysis suite, and how that particular platform or tool is capable of providing the same services or same capabilities, but on a cloud-enabled, in a cloud-enabled way or environment. Okay. So for the outline, there is some motivation and background, and we are going to talk about a little bit about incrementality and reactivity. What does it mean, and how I or we who created this presentation and also the tools behind them understand that. Then we will check the different realization options that are available, what VIATRA is able to provide, and maybe some of the add-ons or additional features that might be interesting for those who are willing to move forward their research into this direction. Then I will talk about a little bit about some evaluation, some runtime performance characteristics, and the closing thoughts will be about IncQuery suite. That let's say that's the future in our company's roadmap. VIATRA is still there as an open source solution, but as a commercial product and service, it's the IncQuery suite that is capable of scaling up to the appropriate number of model elements in the ranges of 10 or 100 millions. Okay, so reactivity and incrementality, because based on my experience, it's always better to specify what do we mean about certain of these phrases or definitions, as it helps to have a common understanding. What does it mean? It's a reactive transformation. What does it mean? It's an incremental transformation. How do they relate to each other? So if you get to a simple scenario like this, we have a source model, and we transform it into something called a target model, and we keep some trace information between them. I think that's the most basic way to describe what the transformation is usually. As you can see in this example, we use some kind of sequence diagram as the source, and the target is something like something else, not that important. If we extend the particular source model, we would like to make sure that when we are transforming that particular part, then everything will be according to the specification of the transformation. But how that actual transformation is executed, that's the big question. And these are the points that we are going to talk about. The problem usually that we face is that the source model can be quite huge. Let's consider if we are, let's say, in the system engineering domain, there is a well-known example, the 30-meter telescope. It's on GitHub. It's a huge system model provided by the NASA guys. And it's, as far as I can remember, it has more than 1 million nodes and a couple million references in it. So, and this is just one particular model. And as you can imagine, even in the NASA domain or the space domain, there are even larger models available. So the size of, in the range of 1 million, couple million, or even 10 million model elements is not, something rare or super unique. The other requirement that usually people are willing to look after is the execution time. Nobody would like to wait for days, especially if, for example, the transformation is driving some validation, or we would like to provide some feedback. If we can shorter the feedback cycle, it is better for the engineers to work with. They would have the results faster and be able to react according to the analysis result, for example. And the final requirements that usually happens is that if things are going well, we would like to chain our transformations. So it's not just like a simple source to target transformation, but maybe the target itself, target model itself later be, or for some reason be part of a chain, and it will serve as an input model for another transformation. I think the simplest example is if we have a high-level model, let's consider it system block diagram or something like that. We generate an AST from it, and from the AST serialize or generate, let's say, a representation, like say in XML or something like that. Then we have multiple steps, and it can be executed as a chain of transformation. So if I change one thing in the high-level model, I would like to see that the change propagates through the whole chain, and the final XML serialization is also updated as soon as possible. So what does it mean in our understanding, incremental transformation and reactive transformation? Because in a certain sense, they have quite a lot of commonality. Whenever we are talking about transformations, we're talking about one-way synchronization. That's important to state from the beginning. So we are only thinking about changes happening in the source, and it needs to be propagated to the target. And so there are two definitions that we usually use. There is source incrementality and target incrementality. We use it, as you can read there, that source incrementality means that read as little as possible. So it relates to the source model sizes, what is the context I need to process in order to see the changes. Target incrementality means that rewrite as little as possible. So in certain cases, if I need to redone the transformation, how much of the, let's say, the already transformed model elements can I keep, and how big is the portion that I need to regenerate. And yeah, training requires both. What is more interesting, if we go a little bit further into this direction, what does reactivity means? Reactivity means that if I receive a notification, so I need to react to changes happening in the model, I first need to understand what has changed, which, as you can see, is related to a kind of incrementality, and then receive and then be able to define what to do in that case. So in reactivity, in a certain sense, I rely on the capability to understand what has changed. Either I receive this information as precise as possible through notifications or whatever mechanisms, event stream, through an event stream, I would say, or it can be as simple, I just receive a dirty bit, something happened here, and I need to do the calculations to see what has changed in the underlying model. And based on that information, then I can react to these changes. So reactivity in this sense represents these 2 or 2+1 problems. I need to know that something has changed. I need to understand or compute or realize what has changed. And then I need to be able to react to these changes and provide or define my rules according to what has changed. So these are usually in conceptual in the reactivity word translated into events, event stream, which in its own defines 2 things. Change has happened, and the event itself described to a certain level what has changed, and then the rules are driven by these changes. But we need to note that even an event can be, separated into a real notification, something happened, and then the calculation behind that will provide information what has changed. Okay. So with that said, I would like to describe 4 different approaches that in a certain sense fulfills some of these segments or parts of reactivity. It is able to calculate the changes, it is able to react to that, or it is able to really automatically react. So it receives information that something has changed and can autonomously, let's say, in a certain sense, refresh the target model. I think we will start with the simplest stuff, which has nothing to do with that, just to have the common ground for everybody, which is the batch transformation. Now, source 1 and source 2 represents the same model, just different segments, okay? So it's one model. I would consider the source model 2 different segments. And I do the transformation first. Usually that's quite simple. I will create the according to the specification of the transformation, the target 1 and target 2, and we'll have the traceability between them. Very nice. There is a change in the source model. In our example, always source 2 will change. Then in a batch transformation, what will happen? I need to re-execute the transformation from scratch because I don't have any capabilities not to do that. So in this sense, as you were able to see, I delete everything what I already had and just simply re-execute it, and then the updated target 2 segment, let's say, is created, and also the trace and everything else is created. However, I have redone the whole work for target 1 and trace 1 for sure, and a large portion for target 2 and trace 2. Okay. Well, if we move a little bit away from this story, then there is, let's say, the dirty bit. I call it the dirty bit approach, which means that as a first step, I do the transformation the same as I did. Then the source model changes. I receive, let's say, for that segment, if they are stored, let's say, in a different file, for example, or something like that, I receive a dirty bit information that that particular model segment has changed. And due to this, that I receive this information, I know that I don't need to touch, let's say, what is in source 1. I just only need to re-execute everything what is stored or represented in this simple example in source 2. So I need to re-execute the transformation there. Yes, I know what happens if there are links going through between source 1 and source 2 and stuff like that. But technically speaking, this can be done. And and represents a little bit better solution, because due to the re-execution, we didn't have to touch anything what we have already done for trace 1 and target 1. Okay, so this can be considered as a kind of coarse grain incrementality, because let's say it's in a model segment or file level. It is, if we really listen to the dirty bit mechanism, so let's say that I know that the file has changed, this can be a kind of event source to which we can attach our reactivity. But I think nobody is really considering this approach as a kind of reactive transformation, because it is quite cumbersome. Usually it still requires a lot of transformations, because if I cannot separate the source models properly, then I need to regenerate a lot of stuff, and also chaining and cleanup can be quite problematic. So we need to go a little bit further like that. I call it reactivity by traceability. Let's call it like that. So the first transformation is done. I won't animate that anymore. Then the source model changes, and how we define our transformation itself, and that's an interesting thing, is that it detects, or it is looking for missing traceability links. So the idea is not that we create a transformation that directly works only with the source model and then create the target, and then creates the target model. We have specific rules that are looking for, let's say, missing traceability links. It is related to the source model, but it looks for those missing links. And how I define my whole transformation is that, okay, if I have these missing links, I would like to see what are those elements that are not connected, or not that they don't have tracing to the target model, and then re-execute the whole transformation or these specific rules to that particular segment of the source model. Again, this is quite useful. It knows a lot, in the sense that it only if the rules for the trace-based rules I'm able to provide a fine granularity, then it doesn't need to do a lot of additional retransformation or re-execution of the transformation. However, it's still not a superb solution, because it still relies on a kind of triggering mechanism. So when do I activate these kind of rules? How it should be working depends on the model storage. It can also be attached to this dirty bit, which is quite simple. Or maybe if we are, for example, using CDO and we have a transaction mechanism, that at the end of transactions we are able to use that as an event stream, and it will always send us the appropriate signal that, okay, this is the time, do your stuff. Based on the missing traceability links, we execute the appropriate transformation. We will have the target. Okay, we are in sync. We can continue with executing the commands, waiting in the command queue for the source model. Okay. The problem is that depending on the trigger mechanism, it can be quite strong or weak with respect to reactivity. And the quality of the traceability links is a big question in this case. Even with the best intention, if the transformation designer and metamodel designer at the first glance are not thinking about using this approach, and the trace models are already there, then it can happen that it misses some of the necessary information to be able to work only on the missing, let's say, part of the trace, and for that reason it might require a lot of reading within the source model or a lot of regeneration in the target model. So it depends heavily on the traceability links quality, if I can say, or how verbose those traceability links are. And also querying needs to be quite smart with respect to speed, so runtime performance, and also to express what am I missing in this certain sense. Okay. No, and let's say we arrive to something that we consider or in our terminology, I'm calling it now true reactive transformation. It's in a certain sense. And this is just yet another interpretation or way to define reactive transformations. But it works in a way like, if I have the first transformation that looks the same, then the source model changes. And what we are really looking for is new activations. And I will dig deeper into that. What does it mean? It means that I have defined my transformation as rules. These rules are defined as graph queries or graph patterns as their activation part. And then there are command rules, what to do then. And these activations are based that a particular graph pattern or graph query has new matches, or some of the matches are disappearing, or let's say certain attributes, if we go into detail, certain attributes are changing within this result set. So it means that I'm looking at my model through the graph queries I have defined. I have defined these queries to drive the transformation itself, so I know I need them. And I'm looking for what is happening with the result or result set of these particular graph patterns. And these changes, appearance and disappearance of new matches or some change in their attribute values, are the input for my transformation rules. So I can say that if a new match appears here, do this. If it disappears, delete, blah, blah, blah. If the values change, I don't know, regenerate that part. If there is a new name or whatsoever, do that or that. And this way, I can make sure that this kind of reactivity really works, because I have a triggering mechanism. Changes are happening in my source model, and the details about this triggering mechanism is driven by my rules. If I only have a simple rule, then it's relatively simple and might be activated too often. If it's really sophisticated stuff and I have a lot of graph patterns there, it might be a lot of notification or activations that are happening. And how the activations are not equal to rule execution. So I can wait for all the activations to happen, which means, let's say, end of transaction. I have a lot of activations, and I can say, okay, I will execute all of them in a specific order or in an order that I already defined or whatsoever. So these are, configurations that I can add to the system. So I'm able to say that I was able to detach activations to look what is happening, to understand what is the change, what is the change that has happened, what is the delta that has happened from a 0 point, and then how I will react to that. And usually after I react, I set a new 0 point. So I'm able to again see what has happened from that 0 point and be able to see if new activations happened for my rules. Okay, we will dig deeper into this particular approach. I know it might not be the easiest to understand at the first glance, but it provides all the necessary features and configuration capabilities that we consider as a reactive transformation should be able to do. So this is what is given here. The problem is that still there is a kind of transformation language level restrictions, I would say. So you cannot really define arbitrary. You can define arbitrary transformation, but it might require a gazillion amount of rules. So it might be a little bit complicated to do. Still, for a lot of cases that we have seen in our past years, it's very, very useful and powerful to define filtering, complex filtering or viewpoint mechanisms for a model, and you would like to drive certain, let's say, visualization, validation rules or whatsoever that requires more than just a simple graph query. it requires some additional calculations or changes to the target model. In these cases, it is a really powerful tool and scales relatively well. So these are the 4 different, let's say, ways. I would say one, which is batch, it doesn't matter, 1 + 3 different ways how you can think about some kind of reactivity based on the capability of incrementality, or understand what has changed. Maybe it's better to phrase that. And I would like to show you how that really works within the VIATRA system. So how these high-level concepts are transformed or implemented or realized within the VIATRA framework. For those who are not really familiar with VIATRA, I would say it was really hard to have one summary slide, but I thought that this history timeline, because we are older than 20 years now, might be useful. So VIATRA is a model transformation framework, let's say, that started in 2000, based in Prolog. So you can imagine that was really back in the old days, I would say. And from that point on, from 2004, we have changed to Java Eclipse. And in 2004 to 8, we focused on the incremental graph pattern matching constructs, I would say. Then we have changed the name to something else, EMF IncQuery. Then in 2015, we have changed back to VIATRA. And one of the main reasons to do that was something called EVM, called Event-Driven Virtual Machine. And that is the core or heart that is driving these reactive model processing options within VIATRA. And as we move forward, we have also started within IncQuery Labs, the company, server version, I would say, IncQuery Server from 2017. And from 2019, it has been, I would say, elevated into a product family, and it is more focused on to be able to run within the cloud and be able to scale, adding additional nodes or resources to the suite itself. Okay, there are some links available down. You can check more on VIATRA itself, and also Event-Driven Virtual Machine, which I will now tell about a little bit how it really works. Before we do that, just for the sake of simplicity, all the benchmarks and results and everything that we are going to see are based on something called the Cyber Physical System Demonstrator. There is the link, and all the transformations and examples and everything that I'm going to show you here are available there. So you can check how does it look like, how does it work. You can check the code. You can do your own, comparison of the different approaches. And if you are interested in this, I'm strongly advised to check this particular GitHub page of related to VIATRA. And it's we put a lot of effort to keep it up to date and updated, and it works with the newest version. And also, if you find any error or bug, please report it, as we would try to keep it as a live example or demo of the VIATRA and the EVM platform. So with that said, how does this work? For the batch transformation, we will see 2 different solutions, a simple and an optimized thing. And this is something that is completely created in pure Java, just to have a reference base point to which we will do the evaluation compared to. The batch simple is something that a bachelorate student will do if receiving the task to maybe with a bachelorate degree, so end of his studies. Here is the source model. This is the definition of the transformation. Please create a trace and target according to that, and a normal software engineer would create that. The optimized version is something that you would do with some experience, either from school or from your work, which means that you are using some kind of caching mechanisms, and also we have used some kind of deeper knowledge of the EMF models that are represented in this particular example. So it means that it relies on the utilities that EMF is providing. So it's optimized, I would say. It's still a a plain Java program that is executing the transformation. So not that interesting. As a baseline, it's interesting, but in this context, it just serves as something that to which we are going to measure ourselves. I haven't touched that, but VIATRA mainly works with EMF. Sorry, I forgot to tell you that. So this particular example is always about EMF, and that demonstrator is also a full-fledged EMF model. So everything works the EMF, the in-memory version of EMF. Okay. So what does it mean if we have something called batch VIATRA? It means that the transformation itself is still a batch transformation, which means that when I push the button, it will just read the source model and create the target and trace model according to that, and doesn't really care about what that's changed or something like that. However, it uses the query engine, the querying engine within VIATRA, which is a quite powerful tool, I would say, and especially its incremental query runtime system is very strong or very performant. So that can really help to boost the overall performance. What does it mean? We have the first transformation, so we execute the transformation first, so that doesn't really count. However, whenever the source model changes, as the query engine itself is already incremental, it means that the notification sent by EMF itself, let's say, as we are populating it with some additional listeners, we will know what has changed, and the query engine is able to update its result sets. It doesn't really affect the transformation itself, because we still need to push the button and thus re-execute the transformation. What it does, that in case of re-execution, everything is deleted and recreated. However, as the query engine is incremental itself, whenever I'm reading the results coming from the query engines, I will already have the new version, which means that the querying time, the query execution time, will be close to 0 or a couple of milliseconds. And usually the bulk of the transformation execution is related to querying the underlying source model. So that's why recreating, it's a batch transformation. It every time recreates the whole model. Yes, it's true. However, due to the nature, sorry, I need to use this. Do you see my mouse?
Yes,
okay.
Yes, we do.
Okay, because I was pointing to my, like a beginner, I was pointing to my screen. So the querying engine is incremental. It means that the querying time, so the query execution time is quite minimal, due to the fact that the changes are what are happening in the source model are sending, let's say, notifications, or we are able to receive those notifications, and the engine itself updates itself just next to the changes within a relatively minimum amount of time. So re-executing the transformation is quite efficient. Still, we would like to move forward. And yeah, this is just a summary on what has happened. We would like to move forward. So let's see how this dirty bit solution works. So we have something called a change monitor, or we had something called a change monitor, and we still have it in VIATRA, which means that we have something, a very simplistic, let's say, solution that is able to work in a way that we have the query engine, we have the transformation definitions, we define the rules themselves, which represents what needs to be done. And if the source model changes, the notification will be sent to the query engine, which is nice. The change monitor is there to read the query result and is able to provide you what has changed from a particular time from a particular 0 point. Okay, provide this dirty part to the transformation, but this is not well defined through an API. It just provides a set of notifications and query result changes, I would say, and say, okay, these are the change things, and the rules are defined in a way that are able to read this change set, I would say, or dirty set, I would say, and based on that, able to calculate on its own the dirty segments and refresh the trace and target model, which means that new parts are created, and it might also require the olds to be modified depending how well the change monitor is configured and how well this dirty part can be explicitly defined. As I mentioned, this is a really dirty solution, and heavily relies on how the change monitor is configured, how it can provide the dirty part, and also exactly how the transformations are explicitly tailored, how would I say, into this dirty segment, reading the dirty segment and understanding what has happened there. So again, not a bad solution. It knows everything if required, but it's a really custom solution and requires a lot of hand coding. Okay, so that's why I still don't consider that as a superb solution. Then we have the explicit traceability based solution, as you might imagine, which means that we have already the EVM, the event-driven virtual machine there, very nice. We define the transformation rules then, very nice, but these transformation rules are looking after traces, the trace changes, what is happening with the trace links, okay? So these rules are based on that. We have a set of rule activations, just as we are in this example. The source model changes. That means that we will see that some negative notifications, some trace links are missing, okay? If you are familiar with graph transformation, it's called negative application conditions. So you can see, you can define rules with negative existence, let's say. So you can say that if I have a source element that doesn't have a connection to a trace element, it means this is the pattern I'm looking for. So my so my match set will be updated according to that. So I know that these missing links are problematic for me. These changes will update my rule activations because new pattern activations are available, and I can fire away the appropriate actions related to these match sets. Okay. So the difference here compared to anything else, that when we are defining R1, R1, R2, and R3, we are explicitly focusing on to look for these missing trace links. So this is the mindset how we define our whole transformation. And at the first time, there is only the source model, so it will have a lot of activations, because there is no trace link, and then I will have to get to the point where it's in sync and then be able to continue according to this kind of solution. I think this one is still really powerful and useful, and follows, let's say, a lot of common ideas that have been, let's say, around the model-driven engineering community for quite some time. The tracing is important. We should have a focus on the traceability links and tracing the transformation execution between the source and the target. And I have seen others creating transformation based on the same, let's say, principle or idea that what we are mainly looking for is the missing trace links, and we will define our rules according to that. Yeah. So it is already using the EVM, our event-driven virtual machine. The rule activation lifecycle is managed by EVM. as I mentioned. It provides you a very simple, at the first glance, very simple lifecycle as a default. So appears, disappeared, and changed. These are the three things that can happen with a match that represents an activation. And as I mentioned, one key aspect is that execution triggering is controlled completely separately from activation. So I can define my own execution triggering mechanism whenever activations are happening. Should I wait for a specific, let's say, transaction and kind of activation, I would say, or notification? How do I prioritize between the activated rules? Should R1 always be executed before R2, or I should select randomly, or I should activate or execute my rules according how they have, let's say, appeared or disappeared. So the activations in time are happening within my EVM. Okay, and this is what it is. And now let's say the final solution, or the final solution. I know I need to be really fast to be in time, which means is that we are looking for something called query-based traceability. It means that our rules are not defined in a way that we are defining what is happening in the trace model, but all our transformation rules are only focusing on the source model, and my activations are driven how these rules that are only looking for the source model are changing. And then in the execution part, we are looking after for the trace and target related model elements. So this is closer to the general way of creating model transformations, because when people 95% writing model transformations, they are always thinking about the source model, and then everything else is usually created, and they don't really care about the missing trace links or whatsoever. They are always checking what is happening in the source model, and this query-based traceability idea is trying to help these kind of people. So rule activations, I would set the 0 point. Okay, so let's say my source and target model are in sync. Okay, that's considered the 0 point. Source model changes. It means that the notifications are sent to the query engine. The query engine provides the information to the EVM what match sets have changed. Sorry. It means that the EVM will check which rules are attached to certain match set changes. Something appeared, something disappeared or changed. Based on that, it will create the new activations, which we know how far are they from the 0 point. In our case, the black 0 and the gray 3. Sorry, the black 3 and the gray 3. And then, based on how we define the activation, rule activation or rule execution policy, sorry, we will execute these particular activations. And then we will set out a new reference point. So now we know that the source and target models are in sync. So we can tell the EVM system that we are in sync. So that's the new 0 reference point. And then the transformation can continue. So if a new change is happening, the same game can be played again. And my gut feeling is that this, at least how we are able to provide, reactivity, this is the most, let's say, this kind of approach has the largest set of features that are usually required for a reactive transformation. Okay, and as I mentioned, within the EVM, we have a kind of implicit traceability that is coming from this match set changes, and with respect to the 0 point, the reference point that we are defining. Okay, and yes, you can create trace links in order to have a proper source trace link target serialization or representation of your models, but it's not necessary. It's not necessary. Okay. And what is nice that VIATRA itself provides what is there in the middle, and it provides a proper API with extend if you're an old school Eclipse guy, or also Java 8 compatible API, proper API, and you can use VIATRA patterns, graph patterns to define the queries to which the validations are driven, and then the action part related to the action parts, what to do in Java, and the EVM API provides you this possibility to define what to do when, for example, in a rule, what to do when a new match happens for a query. This is this is a special operation to do there. What happens if it disappears? Other kind of action, and what to do in case attribute values are changing in the appropriate E objects. Okay, so this is what has happened, and yeah, it is part of the engine for quite some time now, and it has been used in several industrial projects, so its maturity is quite high. So a couple of words on the performance. I wouldn't want to go into details, but it's a decent model. As you can see, the largest one scales up to 120,000 E-objects and 4.5 million references. Okay, we have a complete description about that, and we have executed it in a decently powerful desktop machine with 16 gigabytes of RAM, and we have executed with all the different solutions that I have described in the last 30 minutes. Okay, which means that the first, it's a logarithmic scale. What is important that in the first transformation execution, the really heavyweight traceability solution was still, in par with any other solutions. But what is more important, so within 200%, so 200% within the first execution. But when we are doing re-execution, that's the most important or interesting part, I think, in reactivity. So we are reacting to the changes, and that's the time that we would like to be fast. As expected, let's say these reactive approaches are able to update or synchronize the target model within a couple, let's say, couple dozen of milliseconds, and that was something that we were really looking forward to. So from incremental graph querying or pattern matching, based on the EVM and all the other solutions, we were able to scale up to, let's say, reactive transformations, which are also able to, if the changes are not happening too often or they are not too large, to have a really decent under 100, let's say under 100 millisecond response time. I think, which is quite a nice feature. Yeah. So the conclusion on the VIATRA part is that we have the VIATRA EVM. It is part of the VIATRA Eclipse open source stack, and you can try it out on EMF models. So that's quite useful. What is also interesting that we have something called VIATRA for Magic Draw. So there's an open source solution that you can use also this same technology stack in Magic Draw as another platform. Because I won't tell you, but under the hood, with the Magic Draw, they're also using their own implementation of EMF. So the models can be viewed as EMF models, and that's why it was not that cumbersome to adapt our transformation engine there. And the CPS demonstrator is help to see which transformation approach or how to use VIATRA in your own case, what kind of rules or what kind of way you need to configure it if you would like to achieve some kind of incrementality or reactivity. So it's there and open for everybody. Just a couple of sentences for the future. The IncQuery suite, which there's the web page for that, IncQuery.io. And the idea was that to elevate from a desktop solution to a, let's say, a server and then to a cloud-based solution, that provides the same capabilities, just with a lot of additional engineering work and research in order to be able to scale up to large problem domains, okay? And provide these unified search, analyze capabilities over a larger called digital thread, which means the separate silos in which the engineering models are sitting. So that's the core idea behind IncQuery Suite. It's a product, it's already on the market for a year or two now, and we are having the first customers. The main idea behind is that this is the underlying technology that provides these nice looking features like validation reports, analysis dashboards, querying capabilities, and where really the heavy lifting is done and sometimes this reactivity is required is the tool integration, where you will have to synchronize between different kind of representation of the same, let's say, information, different kind of model representations, okay? Yeah, the tool itself is integrated to quite a lot of different, let's say, modeling solutions, I would say. It's not all of them are backends, but solutions. And this is just an architectural overview. How does it look like? The server itself, it's not a repository or anything like that. You need to have a modeling repository, tool or whatsoever that you are using, in which you store your information, and the server itself attaches itself to this repository, reads the model, and if the repository supports, update itself according to the delta that the repository is able to provide, or if it does not support that, either you are always reading, always writing through IncQuery server, then it can, keep itself updated, or if that's still not possible, it needs to sometimes read through the whole repository to update its cache sets, and then here within the server you can serve either the OpenAPI that is provided for a lot of services, a Jupyter Notebook, let's say, solution, which helps to run queries and transformations and see what is the results. And also we have, a really end user facing web console in which you have a more decent user experience seeing your own model. And in certain situations, we have the desktop integration, which is there for, I would say, any kind of Eclipse tool with some adaptation cost, but also out of the box, it works with the Kamau system or the MagicDo platform. That's all. Thank you very much for your time. And if I have, I don't really have much time for questions, but
yeah, let's see if we have a time at least for one.
Okay.
Some time for one question, quick question. Otherwise, we can quickly move to the next
but I think I was almost in time because we started at 05, so and I'm finished at 20, so that's not that bad.
Any question? No? Okay, so I will very, very quick question. So concerning can you say something about the overhead added by this always running process to detect events? Because essentially now you have implemented kind of you detect the events, and according to the change you perform some actions.
Yes.
This means that there is a process always running. So do you think, according to the figures that you have shown, it seems that this overhead does not have an impact to the
it has to be honest, you are buying runtime for memory. So all this stuff requires a lot of memory altogether. So I think this is the most important thing to realize, that yes, you can be really fast if you are caching smart, but the cache requires memory. So you are paying with memory for your runtime performance. So this is what is happening. This kind of, let's say, loop that is coming, it's something, let's say, that is already provided by Eclipse. So we haven't wrote down like while true or something like that, and it's an infinite loop. We are listening for the the base EMF notifications, and whenever they are happening on your thread, the execution will get to the VIATRA part, and then it will do its part, to update the caches and whatsoever, and then create the activations, and the activations themselves are using the same kind of notification mechanism. So when the the appropriate, I would say, service is called, then it receives, okay, what are the new activations, and then based on that you can run them. If the action part of a rule is long, then it will take some time. So it depends how you formulate your rules. That's the trick or the magic there.
Thank you very much, Akos. So it would be really great if you could also share with me the slides so that I can make them available to the students and our attendees. Let's move to the next speaker. Thank you, Akos. So I'm very happy to have today Artur Borna from, he's a lecturer at the School of Informatics of the University of Leicester, UK, and he's going to present YAMTL, the YAMTL model transformation language in order to manage model-to-model transformations at scale. I'm very happy to see Artur. I don't know if can you try to share your screen, Artur? You're muted. Can you unmute? Yeah.
So the button kept moving, so I was chasing it. Now I can share my screen.
Yes, please. So thanks for having accepted the invitation.
Thank you so much for the invitation, actually. And I suppose that you cannot see anything now, right?
We see only the desktop.
Okay. Can you see?
Yes, now yes, we see the slide. Yeah.
Okay, that's great.
So the stage is yours.
Thank you, David, and thank you for the invitation again. I'm going to present the model transformation language YAMTL and some of the its use cases in this talk. I'm going to start with the main use cases in model-driven engineering, where model transformation technology can help in the development of low-code software development environments. These involve model transformation and synchronization, which have already been presented by Akos in the previous talk. So that talk has been a very good preliminary for this one. Typical examples of model transformation involve the automation of software production to lower development to lower the development costs while improving quality assurance. In this case, citizen users normally work with domain-specific languages in a low-code development environment by modeling abstractions in a specific domain and by skipping implementation details. For example, in a software architecture, we can design it by using a component diagram. Such models are then automatically processed by a model compiler to generate code, or they are evaluated by a model interpreter to animate the model. Model transformation is the enabling technology that allows the design of model compilers and of interpreters, encapsulating technical expertise and implementation decisions, which are hidden from the end user. Model transformation can also be used to infer knowledge from legacy code bases, as in the example of the reverse engineering case study that was mentioned earlier this morning by Antonio. And in this case, we need to use model transformations in combination with model-based parsers. In the reverse engineering use case, the data in the legacy code base is represented as a very large model, which can then be analyzed by using model transformation technology, that's why it's important for model transformations to be able to deal with very large models. Another common use case is when we deal with software systems that consist of heterogeneous models. When working with low-code development environments that enable the design of a system from different views, these need to be kept consistent. When changes are applied to model view, the user may be given the choice of checking whether the views are still consistent, and if not, inconsistencies can be reported with an informative explanation and offering quick fixes to resolve them, hopefully automatically. For example, when modeling a component-based system using UML, the components and the interfaces of a software architecture description need to be kept consistent with the object models that describe the internal structure of the component. And for example, if we modify the interface used at a port, then this change may have an impact in the class of that implements a component, and the consistency needs to be checked. And this is an example of consistency between software artifacts at the same level of abstraction, and inconsistencies can be repaired often automatically using model synchronization. Models are also used to document both to document software systems and to generate parts of them. The first time a model is compiled, the model and the resulting code are consistent or synchronized. And at a later stage, as we keep maintaining the system, either of them can be modified by potentially introducing inconsistencies. And those inconsistencies need to be resolved in order for the documentation to reflect accurately the design of the system. This is normally done by propagating changes either from model to code or from code to model. Model transformation technology can also be used for implementing such model repairs using synchronization mechanisms, as Akos was explaining in the previous talk. And synchronization has the advantage that the computation that is done in a model compilation is almost entirely reused for the parts where the change is applied, thus enabling a scalability with respect to the amount of the changes that need to be processed. Very large models, in this case, I understand that very large models means that they consist of millions of objects, as in the reverse engineering use case, or as in the VIATRA CPS benchmark, have been made available with the application of MDE in industrial case studies and also in research-oriented synthetic case studies. And these case studies have been used for exposing the limitations of serial model transformation technology. During the past decade, research efforts have focused on parallelizing and distributing model transformation technology using cloud infrastructure in order to overcome this problem. Many of these approaches are actually presented in this workshop today, that's why it's great to attend it. And focus either on persisting models in distributed model repositories, like CDO or Neo-EMF, and loading them efficiently by fragmenting models and indexing fragments, as in Hawk, by loading them lazily, as in CDO and Neo-EMF. Other approaches focus on executing queries and validation in a distributed setting, like Hawk and like a distributed EVL. And others focus on executing model transformations in a distributed setting, like VIATRA and ATL map reviews. YAMTL was born from the desire to manage very large models in a serial setting that can be used from programs developed in mainstream programming languages, in our case, JVM-based programming languages. The aim was to lay strong foundations for achieving highly scalable model transformations. YAMTL is strongly inspired by ATL, and many of the transformation constructs available in ATL have been implemented in YAMTL. This means that many of the features available in YAMTL should result quite familiar to ATL users. YAMTL offers model-based pattern matching, which can be used for defining queries and for implementing model validation, model-to-model transformations for implementing model compilers, model-to-text transformation, which reuses the functionality of extend for defining code templates. It also implements an internal traceability model, which can be exploited for executing model transformations incrementally. And it offers a forward model change propagation mechanism, quite similar, to some extent similar to what to the mechanism that Akos was presenting towards the end of his presentation. And this forward model change propagation is used for executing model transformation incrementally. YAMTL is primarily a model transformation technology that consists of an internal domain-specific language of extend, and it's also an execution engine made available within the JVM ecosystem as a Java dependency. YAMTL is completely independent of Eclipse, and this has some advantages if the modeling environment where YAMTL is supposed to be used is implemented at a different RDA platform, for example, as a cloud service. On the other hand, YAMTL is reliant on the EMF API. So in order to load models, we still use the EMF API. Okay? Although we can use this API as a Java dependency outside of Eclipse. For those of you who are not familiar with extend, this is a Java dialect that brings useful syntax and Java extensions to develop Java programs succinctly. And in particular, it resembles, in some parts, it resembles the language OCL, although one can specify side effects too. It's a truly complete language. For the rest of the talk, I'll assume familiarity with extend, but please feel free to ask if you don't understand some of the notation that I'm going to use in some of the examples. As an internal DSL of extend, what we get is full interoperability with the JVM tools and libraries. And this means that we can define model transformations and extend the generic functionality of YAMTL with libraries that are available in Java. And we can also develop model transformations with a YAMTL that can be reused in Java frameworks, like for example in Java EE or in the Spring framework. We are also going to, by using extend, we can also use the high-level API that is used to work with collections, so that we get a query language similar to OCL. And we can also express Lambda expressions with using succinct syntax, more succinct than that of the one that's available in Java. Another advantage is that we can reuse out-of-the-box IDE support for defining model transformation, and this includes a type checker for part of model transformations, and most importantly, a debugger for model transformation. And we don't have to work on that part. We can reuse those tools. YAMTL provides the model transformation abstractions that I have presented in the previous slide, the top Java and extend. So we can write extend programs using the pattern matcher implemented in YAMTL. And we can also, by using YAMTL, we can also benefit from interoperability among modeling tools that are EMF-based using the serialization provided by EMF. One of the strong advantages of YAMTL, apart of its expressiveness, which is similar to that of ATL, is that its transformations can run very fast, as I will show towards the end of the talk. So during the rest of this talk, I'm going to first introduce model-to-model transformation in YAMTL. First, I will provide an outline of the execution model, and then I will present the main part of the language for defining transformation tools. Then I will show how to use model transformations for implementing model-to-model synchronization. And finally, I will present some results with the VIATRA CPS benchmark that has been presented by Akos in order to position our solution with respect to the reference solutions of this benchmark. So let's start with the model-to-model transformation with YAMTL. For this, to present this part, I'm going to use a case study on transforming class diagrams into relational schemas. I'm assuming that you can see my pointer on the screen. Is that right?
Yes.
Okay, great. So model transformations are defined from an input model to a target. So model transformations are applied to an input model and produce a target model, and are defined over an input meta model and an output meta model. In this case, the input meta model is the simplified version of a human class diagram, in which we have packages that contain classifiers. Classifiers can be data types for classes, and classes contain attributes. This should be named feature actually, and an attribute can be typed either with a classifier, which can be a data type in an attribute, or with a class, which would be a reference. And then we want to produce relational schemas that contain a database. A database consists of tables and types. A table can contain columns, one of which is a primary key. And then we will also have columns that are foreign keys, and foreign keys are identified using a naming convention. When the goal of this case study is to apply the transformation to an input class diagram. In this case, we have the abstract syntax of the class diagram, which consists of two classes. The first class has two attributes, and the second class has an attribute that is actually a reference because it's typed with the class. And the idea here is to get two tables, one column for each attribute, an additional column for the primary key, and the attributes that are typed with the class are translated into a foreign keys in the table that corresponds to the class that is pointed by the attribute. In this case, this foreign key is not defined as a column of this table order. It's defined as a column of the item. Okay. Just to provide an idea of the transformation from a graphical point of view, this is not the syntax used in YAMTL. It's just used for illustrating the transformation rules. We have a main rule, class to table, that takes a class and transforms it into a table. And then for each attribute, it will either apply this transformation rule, transforming an attribute that is typed with a data type into a column, or if the attribute corresponds to a reference, that the attribute is typed with a class, then we will get the foreign key column. These transformations, these applications of transformation rules correspond to these transformation rules. This is the transformation rule that given an attribute typed with a data type into a column, and given an attribute that is typed with a class, then this results in a column that represents a foreign key. For defining a YAMTL transformation, I developed for defining a model transformation, we need to define a class that extends a YAMTL module. The name of the class is the name of the model transformation. The YAMTL module is the main interface, it's the facade interface of the transformation engine that provides functionality for loading models, for executing them, and for performing other tasks like profiling model transformations. Then we have in the constructor of the class, we have to declare the header of the transformation. In the header, we declare the managed models, which correspond to the input and output models of the transformations. And for that, we have to provide a name for the model, and we have to refer to the meta model, package, defining the type of that model. And in this case, it's the class diagram is the type for the input model, and the database schema. The database package is the type for the database model. Then we have, in this case, I'm going to present, in this talk, I'm going to present the support that YAMTL provides for model-to-model transformations in mapping semantics. So, or in output, for implementing outplace model transformations in which an input model is transformed into an output model that is built from scratch. YAMTL also provides support for in-place model transformations, although this is still very experimental feature, and it's I'm not going to present it in this talk. Sorry. Then for completing the definition of the transformation, we have a rule store in which we can define a list of transformation rules. Then we have a helper store in which we can define a list of managed helpers. And then we have in the class we can define and we can use any other data structure or method that can be defined in extend, which gives a lot of flexibility. And here we can, for example, import the libraries and use them for performing computations. In YAMTL, a developer can use managed helpers, which are those defined in the helper store, and non-managed ones, which are defined in extend as normal methods. The advantage of using managed helpers is that the result is cached internally in YAMTL, and any subsequent computation will be much faster. Whereas if you use normal extend methods, then the results are computed every time. I'm going to provide an outline of the execution of the YAMTL transformation, and this is split in three main phases: the initialization of the engine, the matching phase, and the execution phase. In the initialization phase, a transformation execution starts with parsing the transformation definition while initializing the internal execution configuration of the engine. At this stage, its type is associated with its extent, so that with the objects that are lived with that type, so that the operator all instances can retrieve all of the instances of a particular type, considering subtype. This is similar to the operator all that was presented by Antonio in his talk. Although our all instances doesn't have this lookup mechanism implemented inside because it doesn't need to access distributed repositories. Static attribute helpers invoked without any contextual instance are initialized during the initialization stage too. And this type of helpers are queries that start with the all instances operation. In the matching phase, the declarative model transformation rules are matched against the input model, and the matches are scheduled for subsequent execution of transformation steps in the following phase. Matches for declarative rules need to be unique and are computed upfront during the matching phase. In the final phase is the execution phase, in which YAMTL creates transformation steps corresponding to matches that have been scheduled, following the order in which they were scheduled. For each transformation step, output objects are created and initialized. So in this case, we have this transformation rule. In the matching phase, this transformation rule is matched against the model transformation several times, against the host model several times. In this case, one match is an attribute that is typed with the data type, and then the execution of the transformation step creates the output object and initializes its features. In its latest version, YAMTL only provides support for static attribute helpers. And those are helpers, those are queries whose values are defined with an expression that starts with an all instances expression. All instances is a YAMTL operation that corresponds to the OCL operation all instances. And for example, we could define a helper that returns the pointer to the string data type object using the OCL, the all instance operation. The search of the, oops, sorry. So in this case, we have that for this type and data type, we get all of the objects of that type. So you should type in, if any, and then we look for the instance whose name is a string. This helper is initialized at the start of the model transformation only once, and then wherever it is used, the cached result will be fetched, and this computation doesn't need to be performed again. The YAMTL rule consists of an input pattern and an output pattern, both of which can contain multiple elements. YAMTL borrows the concepts of matched rule, lazy rule, and unique lazy rule from ATL. YAMTL rules can be matched. So matched rules in YAMTL need to be matched by the engine, and lazy rules have to be called explicitly from a particular transformation pool. That means that declarative transformations in YAMTL are defined using matched rules, and then you can also specify imperative model transformations using lazy rules. We have two types of lazy rules, as in ATL. We have normal lazy rules or non-unique lazy rules, with which we can create a new transformation step every time they are called. Whereas unique lazy rules are always return the same output match whenever they are called from the same execution context. And an execution context is given by a match rule or by non-unique lazy rule. YAMTL match rules can also have priorities, which is helpful for defining control flow between the application of different rules. Matches for rules with high priority are scheduled first. In YAMTL, we also have transient rules, which can be used for performing transformation steps, although the object in the output matches need not be persisted. This is useful when we need to perform some computations using intermediate data structures, which are not directly related to the output model that we want to persist, and this gives some flexibility. Each element in an input pattern can have a filter condition that is applied locally. So in this case, we have an input element that doesn't have any filter. In this second input element, we have a filter that indicates that this attribute, the type of this attribute, needs to correspond to a type that has been matched in the previous element. Filter conditions are local to each element, although we can also have global filters that apply to all the elements. This in YAMTL, in the source pattern of the input pattern of a YAMTL rule, we can program a search plan for finding matches for a given input pattern using dependencies. In this case, we have this with clause with which we indicate that the type element needs to be matched before this element is before the engine attempts to match this element that needs to know. And this is useful because we are going to use the type object that is matched by the previous element in order to implement the filter condition for this element. When no with dependencies are declared, pattern matching is model sensitive, and the elements corresponding to smaller types are evaluated first. And by smaller types, I mean the types whose object extent is smaller than the other. Elements in input patterns can be derived from other matched elements. In this, here we have another rule with a slightly different input pattern, where we have that the first element is the attribute and the second element is type. In this case, the derived with expression obtains the type from the previously matched attribute. And this is, so in this case, the YAMTL engine will only attempt to match the first object, the first input element, and the second one is derived. All of those elements that are derived are always computed after matched elements, and there is no need to specify with dependencies. In this case, this is helpful in order to avoid to reduce the amount of computation performed during matching. We have to take into account that we only need to use different elements in the input pattern in two cases, either to disambiguate matches, because matches cannot be shared by different rule applications, or when we want to match objects that are unrelated, so that we cannot derive an object from the other. Otherwise, we can define the pattern with one single element, and that works much faster. So in this case, in the example, we have one single element in the input pattern, and the filter is simply using a navigation expression that obtains the type, and we use an extend expression here for indicating, for checking whether this type is instance of data type. And this is much more efficient than using several elements and trying to match with different elements. In a source pattern, we can also use global filters that are evaluated after all matched and derived elements have been matched, in case we want to define a conditional at the end that applies to all of the matched elements. The fact of having local filters and global filters is very useful in order to stratify the computation performed during the matching of a rule. Although I'm not going to present it in this talk, YAMTL also provides support for multiple rule inheritance, which adds an additional layer of complexity to the way in which filter conditions are evaluated, because we apply first the filter conditions of the super rules. Sorry, I have lost my, okay, sorry, I had lost my image in the other screen that I had. But I'm not going to add that much level of detail. If you want to know more about YAMTL, I will provide pointers to publications at the end of these slides. Okay. And now, let's now talk about how to complete the definition of a transformation rule by using output patterns. An output pattern may also have several out elements, and in the execution phase, an object is created for each element in the output pattern, and it is then initialized with the expressions in the action block. In this case here, in this rule, we are creating a column, and we are initializing the name of the column with the attribute with the name of the attribute that was matched in the input element. Matched objects can be used to retrieve data to initialize output objects. However, target objects created by other rules should not be created from the action block directly, because YAMTL provides a dedicated operator for that I will explain later. When defining output blocks, we can also use using blocks, which are used for initializing variables that can be used in several output elements in a transformation rule. The initialization of the using block of using variables is performed before executing action blocks in the output patterns. And then finally we have an end with block, which is an imperative block that allows the user to perform computations after all of the output elements have been created, in case some additional computation is required. Apart from all instances, YAMTL also implements another operator, which is fetch. It has a crucial role in the language. On the one hand, the fetch operator is used to fetch objects from the execution environment. And for example, in this rule that creates a table from a class, we use the fetch operator for getting the class that was matched in the input element. So in here we're defining the yes. So this is in this rule we have two out elements. We are matching the rule to a class, and we are creating a table, and we are creating a column. With the fetch operator, we fetch the object that was matched in the input element, and we can also fetch the object that is created in the other out element, so that we can define references between objects in the output pattern directly. And the class instance that is fetched from the execution context is used to set the name of the table. The column, primary column that is created in the second out element is used to set one column to the table that is created. And then we have that we can also use the fetch operator for accessing output objects created by other rules when applied to a particular match. In the case of matched rules, there is no need to specify which rule was applied. The YAMTL engine will find the target object. In this, will find the target object automatically. So, for example, here we have the fetch operator is overloaded for collections, and when we have a class is the input class that has been matched by the rule, and we have all of the attributes. When we want to obtain the columns corresponding to those attributes, we will apply fetch, and fetch automatically will find the matches of the attribute to column rule, which is a match rule, and we'll obtain the column object corresponding to it. And then all of the columns that are retrieved will be added to the table. When working with rules, with patterns, with several elements, the full match needs to be provided, and the object to be retrieved needs to be named so that we can retrieve the object for that out element specifically. In the case of lazy rules, we have to call the rule by providing the name of the rule. And in this case, here we have that incoming references is an extend helper that obtains all of those references that point to this class that corresponds to the matched class. And then we explicitly call the rule reference to foreign key column, which will obtain the columns that correspond to those references so that we can add them to the table. The use of fetch in a transformation will affect the way in which the output objects are initialized in the output model. I'm going to skip this part because it may add too much detail, but I'm just using this slide just to mention that YAMTL provides support for multiple rule inheritance, for support for abstract rules as in ATL, and it also provides support for module composition, which is achieved either by extending the class that implements the transformation or by redefining the transformation, which provides some mechanism, some support for superimposition of model transformation. And now let me talk about synchronization in YAMTL. The model transformation used in the first part can be regarded as a definition of a consistency relation between class diagrams and relational schemas. The model transformation implements the model synchronizer in the presence of model changes. This transformation should detect whether the table, the relational schema, is consistent with input table, and if not, it should be able to prepare. The problem here is that executing the model transformation in batch mode, as Apple was explaining, can be quite expensive. And it does not scale with the number of model changes. So this scalability can be achieved with incremental execution of model transformations by simply modifying those parts that are affected by the source change. Given a model transformation between input and output models and the source model change, YAMTL propagates the source model change from source to target by executing model transformations incrementally. This involves an initial model transformation with dependency injection for YAMTL to know which parts of the models can affect the transformation steps of the transformation. And once a forward change is given, for example, the update of a class name, YAMTL applies the change to the source model and then synchronizes the output model with the updated source model. We computed only those parts of the model transformation affected by the source change. The result is an updated model where the names of the table and the primary key and related foreign keys are updated. Model changes are defined with the EMF change model, which means that we can benefit from the change recorder and verify model changes automatically. Change descriptions are instances of the EMF change model and can be serialized and persisted as any other model in EMF. This also gives YAMTL the capability of recording target changes and to undo them if necessary. This is useful for implementing modeling environments where we want to be able to roll back changes. It's quite useful, can be quite useful. By using the EMF change model, we can deal with any change that can be performed to an EMF model, irrespectively of their meta model. This involves creating new objects, deleting them, updating structural features, and involving attributes and references. And this is how we can execute model transformations. Very briefly here, and now skipping first the incremental execution part. In order to execute the transformation, we first need to instantiate the module class that defines the transformation. Then we load the input model, and this is the name of the model in the header, as used in the header of the transformation module. We set the path to the model, and then we execute the transformation, and finally we save the output model, providing the name of the output model as defined in the header of the transformation. If we want to execute this transformation, the only thing we need to do is to set the execution mode to incremental, and then we have to either load the delta if it's persisted as an XML file, or we can, if we don't work with the EMF change model, we can simply provide a lambda expression that indicates what are the side effects that need to be performed. And the side effects can be described in Java, or in this case in extend, indicating that the change to be performed is to change the name of a class in this case. The record delta operation observes the change, defines the change description as an instance of the EMF change model, and then it reverses the change so that at this stage, before executing the transformation, the source model doesn't have the change applied yet, but we have recorded the delta. And at this stage, we can propagate, when we invoke the propagate delta operation, the delta with the name delta name that is applied to the model CD will be applied to that model, and the changes will be propagated to the target. Okay, and then this way we can simply propagate the changes that were performed. And you'll notice that we haven't changed the definition of the transformation. So there is no overhead specification between executing the transformation in batch mode or if we execute it in incremental mode. However, I have to admit that if we plan to execute the model transformation in incremental mode, it's important to start defining it, taking that into account, because depending on the optimizations to be performed, then the transformation may be executable in incremental mode or not. And now, in the following section, I will explain some of the experimental results that we performed with the VIATRA CPS benchmark. And I think I need to thank Akros, because now I don't need to explain what this benchmark is about. So I will simply focus on the bit of my transformation. So this case study has been quite a thorough one, and has it showcases many of the features of the YAMTL language. And in particular, we use a helper to determine receiving transitions for performing computations that are repeated in different places of the transformation, so that we can reduce the amount of computation. We also had to use rules with different priorities in order to compute the transitions first and then activate the corresponding transitions in a posterior stage. We also had to use transient rules that work with intermediate data structures that are not related to the active model. And we could exploit the internal traceability model of YAMTL for providing support for the internal traceability, for implementing the CPS traceability model that is expected from the benchmark. For the experimentation, we used the reference solutions that have been explained earlier, in particular the explicit traceability solution and the QRT. It's the query-based traceability solution, which were the fastest at the time when I inspected this benchmark. And last year, we added a solution implemented with ATL using an experimental compiler from ATL to AOF, active objects, that will be presented by Frederick in the next talk. We used an adaptation of the VIATRA CPS generator in order to experiment with very large models with more than 10 million objects. And in the experimentation, YAMTL in batch mode was the fastest for the initial transformation. With the incremental variant, in initial transformation had very little overhead. And here we have, this is the batch execution for YAMTL in batch mode. Then YAMTL in incremental mode was just a little bit more complex, and that's due to the tracking of dependencies. We also noticed that with YAMTL was able to cope with models that were 4 orders of magnitude larger than in the other tools. So, which means that it kind of makes a thrifty use of memory, and we were quite pleased with these results. Regarding the propagation of changes, so the application of source changes and the propagation to the target chains, the incremental variant of YAMTL was very fast, was the fastest solution. There are, for this scenario, which is the client-server scenario, in other scenarios, our solution was in between QRT and the explicit traceability. So there are other scenarios where YAMTL was not the fastest for updates, but still we were quite pleased with the result. The reason why YAMTL sometimes is not the fastest in updates is because the incremental execution of model transformation steps, it's not fully incremental. The action blocks for output in the output elements of the output patterns are not fully incremental, and there is some redundant computation there that is still different, which is why sometimes it's a little bit slower than the fastest solution of the VIATRA CTF bench. So in summary, YAMTL brings declarative model-to-model transformations to the extend world using advanced model transformation constructs, provides support for very large models with very good performance, and it provides incremental model and provides incremental execution of model transformations, providing scalability with respect to model changes. These are the publications, and this tool is available on GitHub. You can feel free to use it and let me know if you have any questions about it. So thank you very much, and this is the end of my talk.
Thank you. Thanks, Arthur. Thanks for the great talk. Any questions from the audience? No questions? So Arthur, just a very quick question because we are already, late with the schedule. So what's next now with this language? So what do you plan to do now?
Yes, so I'm currently studying these redundant computations that are performed when we execute model transformations in incremental mode. And I'm trying to minimize them by increasing the number of helpers that can be used. So most of those computations are of redundant computations because we are using unmatched helpers, which are helpers implemented as extend methods. And currently I'm working on making those, providing support for matched helpers that can be applied to specific contextual instances. That's the most immediate approach.
I see. Yeah.
And future work also involves the parallelization or vertical scaling of YAMTL model transformations by parallelizing the matching phase and the application of transformational steps, taking into account using multi-threading techniques.
Okay, thank you very much. Thanks again for the talk. And as for the previous speakers, if you can share with me the slides so that I can make them available for our students.
Sure.
So thanks a lot.
My pleasure.
And yeah, it's now time for our coffee now. Yeah, I would, in order to not delay too much the next presentation, I would take 10 minutes of coffee if you agree. So we can meet at 3:20. Okay. See you soon then. Thanks.
Cheers.
Test.
Hello.
On t'entend bien, Frédéric.
Merci. C'était pour vérifier si tout passait bien.
Oui. Le français pas super bien. On va voir en anglais.
So I think that it's 20, so I think that we can start. What do you think?
It's okay for me.
Good, good.
Yes.
Okay, thanks. Let's start this session. Yeah, it's a pleasure for me to have Frederic and his colleague Theo that are going to present their work about ATL, an extended declarative ATL. And yeah, Frederic, the stage, Frederic and Theo, the stage of yours is yours. I don't know how you are going to manage this session together.
Thank you.
So,
thank you. So I will start the presentation, and Theo will continue presenting the tools. So hi everyone, I'm Frédéric, and the work we are presenting today with my colleague Theo Le Calvar is about how we have extended ATL with incrementality and support for constraints and constraint solving in order to achieve new possibilities. So model-driven engineering problems sometimes need the tools to search for solutions. So you typically have a model, a set of constraints, and you need to find a solution. One example, for instance, would be scheduling. So you have a model with the tasks and dependencies between these tasks, and you want to find a possible schedule that respects the constraints between the tasks. Another example would be finding the right elements to complete a model in order to satisfy some constraints, like what you could do in a life cycle assessment. So you have a model of a system, and you have a model of properties of its parts, but you may, for instance, select different kinds of parts. So for given type of part, you may select it, for instance, in wood or in metal, on different kinds of metal, and you may have some constraints that tell you how solid, how rigid it must be. And so this is an example where you would have to search for a solution. So here it would be more in the mechanical domain, but you can, of course, have this in other domains. And a particularly visual example would be the problem of graphical notations, because when you visualize a model, actually you are creating a geometry model, for instance, in SVG or JavaFX, with rectangles, lines, and so on. And you have constraints that must be respected if you want your syntax to make sense, but there are many possible solutions. So you may want a solver to help you find solutions. So all of these kind of problems require a way to search for solutions. And this is typically achieved by translating the problem into whatever constraint solver takes as input. So there are different kinds of constraint solvers. Some will be interacted with using an API. Others will take XML formats. Yet others will take specific textual formats. So it's very easy with model-driven engineering to translate a problem from one domain to another. So translate a model plus some constraints into a textual definition that is suitable for a solver input. So this works. This has been done many times. However, it can be difficult, and it often requires a significant amount of code which also must be correct for it to work. So if each time you have such a problem, you need to write some specific code, you also have to make sure that it works correctly. So what do we need code for? So first, we need to be able to generate the constraints I was telling you about earlier, but we also need to be able to translate the solver's output back into a model. So either by creating a new model, but more often and more interestingly, by updating an existing one. So if I go back to the example of graphical notation, you have your rectangles, your lines, your text, and so on. And you have some constraints that you feed to a solver. The solver computes the location, the graphical location, the geometrical location of every element, and then you just want to update the X and Y of every element so that the solution is correctly displayed. You may want sometime to create a new one, but if you want to have an interactive tool, then you must update the existing model and not create a new one each time. And of course, if you update a model, maybe there are other parts of the model that were not taken into account by the constraint solver, which need to be updated. And also, you may want to be able to take into account changes made on the model by the user, because the user may actually, after seeing the solution, want to change their model. And once the model is changed, you want a new solution, which may entail propagating additional changes and so on. So it's a kind of a cycle. So you don't always need all of these things, but sometimes you need them. And building a solution, an ad hoc solution that does all of this can be quite tedious. So the problem that we try to address is the following. Can we find an approach that can encapsulate all of this while being applicable to different kinds of problems? So the idea is, if we find an approach with which we can define our constraints without having to write all this code, of course, and then whatever we want to do with the constraint models, so the models with the constraints, we are able to use the same tools, then we win, because we require much less code to achieve the same result. So that's what we want to do. So we can already notice that these parts here require some form of incrementality. So that's what I will start with. And then after that, we will look into how to encapsulate all these constraints in a more abstract way. So first, let me tell you about active operations. So active operations are OCL-like operations, so like collect, select, and so on. On each operation has not only an algorithm to compute its initial value, but also a propagation algorithm to propagate changes. So when I talk about changes, here I'm talking about fine-grained changes, like adding an element at a specific position in a collection, or removing an element. And you can chain all these operations in order to build more complex incremental expressions. And when you change the source, you update the target. In some cases, we can also even have bidirectional propagation, but here we are only talking about incrementality. So, as I said, OCL-like expressions with incrementality, each value is wrapped in a box, an observable box, which can either correspond to a model element property or be derived, for instance, the output of a collect or a select operation. And the kinds of box we have come from OCL, set, ordered set, bag, sequence. And we also add one on option. One represents a mandatory value, and option represents a new label value. So we need to wrap all these values because we need to be able to observe the changes. And then every operation has these propagation algorithms that observe the box and when it receives a notification, propagates the change. So here is an example. Let's start with a sequence with 0, 1, and 2. And then we compute a first value, A, which is computed by filtering the source using select. So we select all elements which are less or equal to 1. And then we compute yet another value by collecting on A and multiplying by 2. So for instance, after initialization, we have the source 0, 1, 2. A is 0, 1. 2 is excluded by this lambda here. And then B is equal to 0, 2, because we multiply A by 2. If you add 3 at the end of the source, then it will not change anything, because 3 is also filtered out by the lambda here. So if now we replace the element at index 2, so by -1, so we replace the 2 here by -1, then it will appear in A, and it will appear multiplied by 2 in B. Only if we remove the element at index 1, so the one that was here, we remove it, then it is also removed. So you see that we perform changes on the source and it propagates to the target. And by using all of these operations, we can build incremental transformations. So now I will tell you of our approach to encapsulate all interactions with the constrained models with what we call model set exploration. So the idea is that we want all technical aspects of interacting with solvers to be encapsulated so that we don't need to develop new code each time we have a new constraint problem. So the idea is to consider a constraint model as representing a set of models. So you have a model plus some constraints which define which completion of these models, so assigning value to the constraint properties, would be a good solution. So each element of this set is a possible solution, and the set may actually be empty if there are no solutions. It may be a singleton, in which case we have a single model, or it could be very, very large. And the interaction principles are that at any one time we present a single model to the user, but the user may change the model, for instance, to get closer to a desired solution. So if we go back to our example of graphical notation, you can move elements, and then the solver checks if it is still a solution. Sometimes it may need to repair it if it is not a solution anymore. And of course, we want to avoid unnecessary changes. So we have defined the notion of a set of models that are the solutions, but this set is not defined extensionally, so we don't have all the possible solutions in memory, for instance. Rather, we use this notion of intentional model set definition. So you take a partially instantiated models, so some of its properties have no specific values yet, but you already have all your elements, for instance, and then you add constraints between these properties, and you use a solver to give them valid values. If you want to be able to create elements with the solver, of course, you need to use a solver that is able to do that. The solver's capabilities, of course, will limit the kind of things you can do. But for instance, if you want to have live interactions on a graphical diagram, you want it to be fast enough. But then maybe in some cases, you may want complex constraints. So linear constraints, which can be computed very fast, will not be enough. So you see that there is a trade-off here to select the solver. So here is an example of model set exploration. So we have what we call the model space. So this is the set of all models that conform to the meta model. For instance, the set of all possible UML models. And then here in a dashed line, we have a model set. So this is the set of solutions to our constraint problem. So if we start from the A model, A is just one model in this set, the user may perform a change, and then if this change is outside of the model set, it's not a solution, the solver needs to repair it. So it can choose, for instance, to go back to A, but that may not be very useful because we were already there. Maybe it wants to go back to C, because maybe C is closer to B than A, or maybe it can go to D. And let's, for instance, take the case where D was selected. The user may perform an additional modification And if this modification ends up in the model set, then we don't need to make any reparation anymore because we are already in the model set. So how do we achieve this? Well, we have a model, we have a constraint solver, and we have what we call bridge variables, which connect the model to the model of constraints and the model of constraints to the solver. So a model element property will be connected to a variable in the solver, to a decision variable in the solver. And how does this work in practice? Well, the user suggests an update on the model. This is propagated to the bridge variable, which suggests a new value to the solver. The solver will then update the solution, and each modified variable will be propagated back to the model, which may update the view. For instance, if we look at a view. So we have now seen what is a model set. So how can we generate intentional model sets? Well, we can just take what we had before, consider this as a target, and then start from a source model and write a transformation. So a classical transformation will take one source model and create one target model. Our approach will take one source model and create a model set, a set of possible models, which is defined intentionally as described before. So this is the model set. So we can combine transformation and incrementality. So the transformation has constraints inside of it, so that it can, while it creates the target model, also add constraints to the target model. And then, of course, these constraints can be dispatched to a solver, which will then provide solutions and so on. And if this transformation is incremental, then this whole process can be incremental, which means that you can make a change on the model. This will make a small change in the solver, if the solver is also incremental, which will update the solution and so on. So I will now let Theo tell you about our tools.
So yeah, Frederic talked about the theory and the different things that we want to achieve. And so I will present you 3 tools that each solve one of the problems that we presented earlier. So first one is the Active Operation Framework, so AOF, which is a library written in Java, and which allows you to write incremental expression like Frederic showed earlier. Then based on that AOF framework library, we developed ATOL, which is an ATL compiler that generates Java code that uses this AOF library. And thus it makes ATL code that can be executed incrementally, meaning that if the source changes, then the output will change. And so with this ATOL compiler, we also leverage the fact that we have now our own compiler to make it compatible with plugins. So, and with these plugins, we created ATLC, which is an extension of ATL and allows you to write constraints directly inside the ATL transformation. And so originally we had the ATLC JVM implementation, which runs on ATOL and it uses AOF for the incrementality computation of the transformation and things like that. And it supports several solvers, so Cassowary for linear constraints on reals, and Choco for integer constraints. And it can be used for several applications. So we used it for, to add constraint on the model. So that is used, for instance, if you want to compute a scheduling. So you have your base model without any constraint, with just a task and thing like that. And you add constraints so that the tasks are assigned to periods. And you do it in an ATL refining transformation. This way, your transformation does not generate new model, but it only creates the constraints and binds them to the model. But it can also be used to generate constraint model. And one of the main examples we have is with generating views or generating diagrams. And so that's the path that we followed for the second implementation of ATL C. This one targets the web, and it takes this almost the same ATL-C transformation, which had some nice evolution that were not ported to the JVM1, but it takes basically the same ATL-C transformation, and it generates SVG plus JavaScript. But because this one targets the web, it also cannot be used the AOF backend to compute fine-grained incrementality. So the incrementality of this backend is much coarser. It's basically you can add, apply the transformation rule to new elements to generate new thing, or you can remove elements. But if you want to update, you need to basically re-execute a complete rule application. So it's not as fine-grained as the Java backend, but it's still working. And this one only supports a category, because on the web there are not that much constraint solver, but category is enough for what we target with this backend, which is diagrams. And so that's why for this backend we only have one target meta model, which is the SVG one, which is the main thing because we want to target diagrams, interactive diagrams. And all these tools are available online at our GitHub repository. Yeah. So now I'm going to present basically how each of the tool work and their advantage and drawbacks and a bit of their performances. So first I'll start with AOF. So as we said, AOF is a Java library. So it does not really have any DSLs or things like that. And you can use it directly with an API, but it's not really convenient. So we developed several embedded DSLs in Extend, but they were not really usable. They were not very functional. So for instance, below we have one of how it can look like if you write it in Extend. So for instance, the first line target underscore IP binds the property IP of the target meta model to the property node IP to the source model, and it do it like that. But you can also have more complex expression with collect, select, and things like that. But as you can see, it's not really nice. It's a bit complicated, and it's very low level. But it's, yeah. So I'm going to present the performance. So again, we are using the CPS to deployment benchmark that were presented earlier by both presentations. So thank you. I think we can just skip this slide and go directly to the results. So this is a quite old result. So it's before the new YAMTL. We don't have the YAMTL time, but now that we can see is that AOF perform basically it's very similar to VIATRA, both for time and memory. So this is time, and the next one is memory. So yeah, this is very simple. We also have another benchmark from the TTC 2018 live contest available at GitHub, but I will skip to AOF. So yeah. So as I said earlier, the AOF framework is working. It's working nicely. It's quite efficient, but it's not very user-friendly because you can write some embedded extend DSLs or something like that. But actually, ATL is a very used, yeah, you need to have some kind of more user-friendly surface language. So that's why we chose to make an ATL frontend for AOF. And that's what ATL does. It takes your ATL file and compile it to AOF, thus making the transformation incremental. And yeah, and also making ATL incremental allows you to kind of tweak the ATL semantics and new features emerges. For instance, if you do incremental refining mode ATL, then you can kind of specify a derived property that are computed incrementally and updated as you need. But in the meantime, you need to be careful because if you are not very aware of what you do, you can easily make circles and things like that. So it's supported, but it's not very easy. Again, this is the result with only in incremental VIATRA because we didn't have YAMTL at the time. But yeah, same as the old one, we can see that we are basically very similar to the incremental, both in time and memory. So this is the initialization time. You can see that we are basically on par with the batch version of VIATRA. And we can see that the ATL, which is generated code, is very similar to the AOF. But on the modification time, we can see that we are not linear. What YAMTL was, so it was better on that side. But again, we can see that we follow a similar growth than to increment that to VIATRA. And this time we can see that there is a slight difference between generated code from ATL and manually written AOF time. We can see that the ATL file is not as good, but still it's scale basically very similarly. And again, now with the full workflow, we can see that we have basically the same slope, but we are a bit better than VIATRA. And now for the memory, we can see that we are basically the same as incremental VIATRA execution. And the full benchmark are available online on GitHub. Yeah, so as I said, there are some limitations with ATL right now. So we only support a subset of ATL because it was because not all parts of ATL make sense in an incremental ATL. So for instance, imperative parts of ATL are not very can be a bit complicated to understand what they do, how should it be updated and things like that. So we stick to the declarative part. We do not support the matched rule, so we only support the unique lazy rule. And thus we do not support the guard too, because when you explicitly call your rules, you don't necessarily need to support the guard. Oops. Yeah, and also we have some semantic differences on the OCL part. So we chose to do the implicit collect, which is supported by OCL, but not by the ATL one. We also added the possibility to reference specific target element for reference rule. So in classical ATL, you only get the first one implicitly, but you cannot access the other one. So in our backend, you can choose the one you get. And as I said earlier, also we have the refining mode transformation, which allows us to write derived property directly in ATL. And so now that I presented the AOF and ATL, I'm going to present the ATLC. And I'm going to present ATLC on one big example and just two small examples later. So this example is you have a single underlying UML model, and you want to have a visualization of this model. And so here we want to have two visualization, two projections in a sense of the same model. So one class diagram and one object diagrams. But because you have one underlying model and two visual one, this means that if you want to have a proper visualization, it means that if you want to change one of the visualization, then you need to propagate the change back to the underlying UML model and then propagate the change back again to the other view. And so I'm going in the next slide to present how you can perform this. So first I'm going to only talk about the classical part. So if you would do normal ATL, classic ATL, then you would write something like that. So you would have a rule that takes your class, UML class, and that generates several elements. So for instance, here we generate a rectangle, a text, a line with their property correctly defined. And we also have a figure, which is a special thing that is only used to encapsulate everything into a simple element that can then later be easier processed. So this is not strictly necessary, but it's easier to process. And then again, for the property, we have a very similar rule. We have the input ATL, but then only the text with similarly only thing like that. So this is normal ATL, but the thing about this is that this normal ATL does not contain any information about how to place element on the screen. So what you would like is something like on the top with the elements correctly plastered, one to rapport to each other. But since you did not state any constraints or thing like that, then you don't have any way to ensure that they are placed like that. So they could be placed like that. It would also be a valid result of the transformation. So what you need is you need to have some kind of geometric sense. And by geometric, here we will focus with constraints on the micro layout, which is how the basic elements are placed in next to each other, and not in the whole sense how each bigger element that is constituted of this smaller one are placed on the screen. So for instance, we want the text to be placed correctly corresponding to the rectangle it contains, but we don't really care where the visualization of the object is on the screen. So micro layout is the small thing and macro layout is the placement. So this is, then we have a set of constraints that we want to validate. So we want each element to stop moving, or at least to try not to move if not moved. We want the rectangle to be as small as possible. And we also have a lot like that. So we want to, yeah, we don't want this to go on the other side of the screen. And we want to center the text inside vertically. We want to stick the text on the top and so on and so on. So we have all these kind of constraints that we want to be validated at any given time. And so to achieve that, we will add a part to the ATL transformation. And then this part is where we specify constraints. And here we can see that each of these constraints that is written in the English language is then translated to one or several constraints in the constraint sense, which are basically just OCL expressions that are evaluated to Booleans. But because we compile it on the other way, instead of evaluating them and generating Boolean value, we enforce them by compiling them to constraints and giving them to a constraint solver instead. So this is the idea. Then I will just showcase two very newer examples that we use on the web. So for instance, here we have a feature diagram visualization. So again, it is available online at the URL here. So yeah, and we also have another one that is the sequence diagram that is used in AnimUML. And so this sequence diagram also are available online, and they are also defined with ATLC. So to conclude with all the tools we have a low-code solution that is declarative, except for the AOF. And this allows us to reduce the number of line on code overall. And for scalability, we showed that that this enables us to do incremental transformation of large model, and on the other hand, to represent them and do the exploration of large model set, which in fact allows us to manipulate very big model sets, but without the penalty of having a very high number of model elements. And so thank you for your attention, and we are happy to answer all your questions you have.
Thank you very much. Thank you, Frederick and Theo. I don't know if there are any questions from the audience. Any question?
Yes, I will have one question.
Yes, please go ahead.
Yes, just to know about the development of this new version. If ATLC has shares the same code as the original version of ATL, or it's a complete new tool. Whether, I mean, if Frederick reuse its code.
Yeah, so we reuse the same parser. So we did not re-implement a parser so that we make sure that we can parse the same syntax. But we have completely re-implemented the execution. So the old ATL version was generating bytecode for a virtual machine implemented in Java. And for ATL, what we do is we generate Java code directly. And for ATLC on the web, we generate JavaScript code.
I have another question.
Thank you,
Frederick. Another question, Gerson?
No, thank you.
Okay. Another question is in one of the initial slides, I guess in the 11, it was just a representative slide showing when you can generate not from a source model, you generate a model set, possibly a model set. So this means that, no, it's 11 maybe. Yeah, this one, yeah, exactly, this one. So essentially what you say here is that given a source model, you can generate a set of possibly set. I mean, your solution consists of a set of possibly models, no? And so essentially this means that the constraint solver is able to find possibly many solutions. So but this in practice, what does it mean? How are you going to select the solution that you want?
So the selection is performed using the exploration process. So let me go back to the interaction principles. So the idea is at any time you show only one model to the user. So when I say show, for instance, if it's a graphical model, then you can display it. Otherwise, you can just show it with a tree-based editor or whatever. And then if the user wants a different model, what they do is they change a part of the model to make it closer to the solution they want. But while doing this, they may break something because the constraints may not be respected any longer. So then the solver will check if the new solution updated by the user is correct. And if it is not, it will repair it. And so the idea is to repair it while avoiding unnecessary changes. So, of course, a trivial way to repair it is to cancel the change, but then the user does not get closer to their desired solution. So what we do instead is we have we can define an objective function which specifies how to optimize the solution to find the solution that is the closest to what the user specified, and closest in terms of that objective function. This objective function defines how to do that. So for instance, for graphical diagrams, we specify that we don't want to move the elements if it is not necessary for the solution to be valid, which means that if you make a change on one part of the model, it will not move any other parts if it's not absolutely necessary.
Yeah, this was exactly related to, I mean, in the example, the last example about the JFX, no, because in the 2-dimension, no, you can specify the target model, whatever in the space. But essentially, what you're saying, you can, for instance, specify a constraint that say, okay, that the target element should be, I mean, should not be moved from the original position. So essentially, you reduce the solution space by specifying, yeah, exactly, the width and the height. Okay.
Yeah, so actually we have these stay constraints that tells the solver that it should try to avoid moving the rectangle on the text. So it is not to mean that the user cannot move these. The user can move them, but the solver, when it tries to repair a solution that has been broken by a user change, will try to avoid moving them if it's not absolutely necessary. And here, medium is just a constraint priority, which means that if there is a constraint that has a higher priority, this may be violated. And if there are some constraints that have lower priorities, the constraints with lower priority will be violated first. And all the constraints that have no priority are required, so they must be satisfied. On here, we have played with different ways to specify priority. Because stay is an operation, we can add a parameter to specify the priority. On here, because we have a simple equality, instead of trying to encapsulate this with parentheses and so on, we tried to use a simple comment to specify the priority. So it's a kind of annotation comment here.
Yeah.
Okay,
and
thank you. Yeah.
And one thing that Frederick did not say is that the stay constraint, basically what it does is that it creates a constraint that tries to minimize the distance between the previous value and the next one. So that's what it does.
Okay, thank you very much. Any other question? No? Okay, so thanks again, Frederick and Theo, and thanks for having accepted the invitation. So again, if you can share the slides with me so that I can share in turn with our students. So let's move to the...
Thanks.
Yes, thanks, Frederick. Thanks, Theo. Let's move to the last presentation, and it's a great pleasure to have Mira here that is going to present the work about OpenMBEE. And I guess, Mira is going to present, right? Are you going to present alone, or also Lucas is going to present?
Correct, yeah, the two of us will be presenting.
Okay, perfect. So Mira is a software engineering, systems engineering at NASA's Jet Propulsion Laboratory, and Lucas is a member of Boeing's MBSC development team. So I would not take more time, so the stage is yours.
All right, so hopefully everyone can see my slides, correct?
Not yet.
Not yet, no.
All right. Looks like I'll have to give permission to Zoom.
Yeah, maybe, yeah.
All right, I need to quit the meeting really quickly since it needs to restart Zoom. So I will do that and be back in just a moment.
So Gerson, you said that there are questions on your YouTube channel. So maybe we can take this time. Let me see.
All right. Looking better?
Yeah, we can see it now.
Yes.
Yes, it's good.
Perfect.
Yes,
All
please
right.
go ahead, yeah.
All right, so thanks for inviting us to give this talk. I'm Myra Lattimore, and as was mentioned, I'm a software systems engineer at NASA's Jet Propulsion Laboratory. And today I'll be presenting alongside Lucas from Boeing about how OpenMBEE enables the adoption of a model-based digital ecosystem at Boeing and JPL. So today's presentation is divided into about 3 sections. We'll start with an overview of OpenMBEE and kind of discuss the story of how it came to be. And then Lucas and I will talk about how OpenMBEE has been used at our organizations. And then hopefully we'll have some time for a few questions at the end. So OpenMBEE is a community centered around open source models and modeling software. And it was established out of the need for many organizations to create model-based engineering environments to deal with the challenges of building complex systems, and really serving as an enabler for us to transition towards a model-based systems engineering paradigm. So OpenMBEE provides a number of apps and services that we can use to manage models and close the gap between models and engineering artifacts like documents. The core software began as core software released from JPL, but since then it's really grown to include a larger community, which includes more than 400 adopters and contributors from across industry and academia. So we can see a few of the organizations that are active participants in the OpenMBE community. So what does OpenMBE do, and what problems does it solve for us? To answer that, let's talk about engineering documents. So supporting systems engineers is really the key focus of OpenMBE. And today, systems engineers are building highly complex systems, and there's ever more collaboration associated with building these complex systems. And so systems engineers are particularly affected by this because they're very interdisciplinary in nature. So they are tasked with ensuring that the engineering disciplines come together and to produce a system that meets the requirements. So overall, we can say that systems engineers really guide the concurrent collaborative design of complex technical systems. And this is really a difficult thing to do. It's difficult, but nonetheless, we need to do it. So we need our systems engineers to be able to provide leadership through effective communication about their technical data. We need systems engineers who can architect and design these complex cyber-physical systems. And most importantly, we need systems engineers who can manage the complexity of the systems that we are designing today. So systems engineers need to bring all these things together, and even on large teams. The picture that we have here is just a portion of the Mars 2020 Perseverance rover team. And it's no surprise that it takes a lot of people to build a Mars rover. And back in the day, you know, before we had more access to digital technology, document systems were used to do the systems engineering. So when there was a change to the system design, an engineer would issue a memo. That memo would be physically sent to someone who took the memos, reviewed the existing documentation, determined the impact of the change described in that memo, and then published a new document and provided a physical copy to all the engineers involved. So this process for doing systems engineering, keeping track of the current design and the changes was used to actually design the Cassini spacecraft, which went and successfully explored Saturn for many years. So back in the days of Cassini, the cost of creating information was very expensive. So anytime somebody on the team wanted to make a change or create some sort of piece of information, they had to go through that entire memo process. And there was an entire team of people whose job it was to make sure that that information was correct and consistent. But these days, when we're designing systems like the Mars 2020 rover, and we have a team as large as this, because of the digital age, creating information is quite cheap. It's cheap and easy to circulate an Excel spreadsheet, a Word document, or a slide deck with lots of rich technical information. But we no longer really have that group of people that spends all day ensuring that every engineer has the same copy of information. And with the low cost of creating this information, everybody's doing it left and right. And so ensuring that every engineer has the most up-to-date copy is actually perhaps even harder than it used to be. And so what we find, we see it all the time at JPL, and I'm sure you know, other organizations do as well, that a project starts simple. A few people, you know, make some models, create some technical documents, and those people iterate on those models and documents, and then more people are added to the team, more artifacts are made. The project continues to progress through its stages, so the information itself becomes more complicated, it continues to grow, and before you know it, there is an overwhelming number of people mixed with an overwhelming number of sources of information. And perhaps you are this individual in the center that is stuck in the middle of it and can't figure out what is going on, and you're struggling to find and locate the updated information. So this leaves systems engineers feeling like they really aren't doing meaningful work. An example here stating that most of my job is data entry. I want to do real engineering. And it's true that engineers have technical skills that we want to apply. So really using engineers as information janitors isn't the best use of their skill. So ideally, what we would like to do is have less overhead and spend more time doing real engineering work. So we want to spend less time doing repetitive data entry, spend less time figuring out which version is current, and spend less time searching for the information that our systems engineers need. So what's the better way? We have this mess of models and documentation and other artifacts of various versions and completeness, but we can reduce the clutter with direct data syncing. So for example, if we have the right software to if we have some models that kind of are collaboratively developed in a version controlled way, and we generate the documentation from these models, and then we generate and connect it to the other artifacts that we create, things are a lot more manageable. Understanding how everything is connected is a little bit more clear than over here on the left. So when we have the right software to maintain these relationships, our artifacts become connected and it's easier to search and navigate through. And this really is the main concept behind OpenMBEE. So we really want to shift away from the manual and disjoint data management and towards a single authoritative source where we have connected information with and between our engineering documents. And we can see with this connectivity, it's a little bit easier to understand the impact that changes have on other artifacts. So if I make a change in my model, how does that propagate into my document and other artifacts that I've produced? So this is essentially the digital approach to the memos process that was used on missions like Cassini. And I think it definitely should be noted here that this transformation, well enabled by better software, is also cultural. So we all know that engineers, myself included, are still compelled to email spreadsheets around. So it takes some effort to shift to this single authoritative source. But if we're successful, we really can bridge the gap between the engineering work and the additional artifacts and documents that we also need to create as part of our systems engineering deliverables. And OpenMBEE is really helping us do just this. So from the user perspective, OpenMBEE allows us to update once and use everywhere. So if we have an individual who is working on their model of a spacecraft, maybe a SysML model, for example, and we have another individual who is working on a document description about the spacecraft, maybe as something they have to deliver as a gate product. We don't have to worry about data inconsistency between our users because if we're using something like OpenMBEE, we have a way to ensure that everyone is referencing the same information. So the software handles the synchronization of the data, and a user may not even realize that when an update comes their way, the engineer that made that update was working in a different tool. So if a change is made in the model, if we've generated the documentation from that model, the changes that the modeler made are in the document. And if our document is linked to the model, any of the changes that our document writer made also end up back in the model as well. So our data stays consistent. So these are the components of OpenMBEE. I think it's important to note here that OpenMBEE is not just the software platform, but also includes the documentation and examples of how the environment can be used. So OpenMBEE has the model management system, which is the core repository that manages the federation of references. It has view editor and platform for model analysis, which is the document-based interface with its companion that's based on Jenkins that allows you to run executions that update your document. And it includes model development kits, which are how we integrate various commercial and open source engineering tools with the other components of OpenMBEE. There are several model development kits. One of the more popular ones is the Magic Draw or Cameo Systems Modeler model development kit, but there are several others as well. If you explore the OpenMBEE website, you also see some of the other ones that we have. And additionally, you'll also find documentation and training on how to use an OpenMBEE, as well as the 30-meter telescope model, which serves as an open source example. And lastly, OpenMBEE includes the OpenSE cookbook, which is a collection of modeling best practices and examples. So as an open source community, OpenMBEE, again, is not just about the software platform, but also about providing engineers with the information, the example models, and libraries to help get them started using OpenMBEE. So this is an example of OpenMBEE in action. So in this example, we have a system model, for example, a system model of the 30-meter telescope. And we use a model development kit to sync that model with MMS, so the model management system. And from there, we're able to generate a document and publish it with view editor. So users can edit the document and produce a deliverable like the OpenSE cookbook. So we see that the model management system really acts as a gateway for the single authoritative source of information. We also see that the model development kits support the integration with different types of engineering models. In this case, we had a model for the 30-meter telescope. And we also see that the view editor is really there for the consumption of those models. So engineers can look at these models using a traditional document format that engineers might be quite used to seeing. So it doesn't necessarily require them to be experts in understanding the model itself, but gives them a way to see a published version of information in the model. So altogether, these components produce a full functioning environment for doing engineering modeling. Another example that we can demonstrate is in the context of master equipment list, where again, we have MMS as the authoritative source of information. We have a flight systems engineer that wants to analyze the master equipment list, and a subject matter expert who wants to create a report of the master equipment list. So in this particular example, both people can work on the same data that is managed in the model management system, so that the data stays mutually consistent between the two sources. So we actually have a video demoing this. I think in the interest of time today, I'll pass since it adds several extra minutes to the presentation length. But I believe the slides will be distributed and this video is available on YouTube. So you're more than welcome to try it out and take a look on your own time. So as we said before, OpenMBE has really grown into a rich community of adapters and contributors across various disciplines. We've used it at a variety of projects at NASA, as well as other science and engineering projects, with the TMT model being of particular interest, since the model was used to generate completely model-driven documents. Industry has adopted OpenMBE, particularly Boeing, which we'll hear a little bit more about in the next section. OpenMBE has been a part of several standards, including the used in developing the SysML v2 standard. And most importantly, probably the most important thing about this slide is that commercial vendors have adopted OpenMBE. And this is significant because they have built integrations with their specific tools, so contributed to those model development kits and provided users with the capability to use commercially provided tools along with OpenMBE. So in terms of scalability, the first big project that we at JPL used OpenMBE for was Europa Clipper, where there were 100 concurrent users with over 230 documents and decision gate deliverables produced, including 445,000 connections between elements. So the number of connections is really quite important because historically in a more document-based approach, these connections have been pretty implicit. So it's unclear as to where they exist. But now information can be more explicitly connected, and in a sense, this number of connections serves as a representation of the complexity of the system we've modeled. So on Clipper, the positive impact was really the reduction of overhead. In one particular case, they were able to produce an engineering document in about 4 hours, even though it would typically take over a week to produce that same document without OpenMBE. So the benefits of using OpenMBE were quickly realized on the project. Another mission that's utilized OpenMBE, the Mars 2020 Perseverance rover project, where there have been about 50 concurrent users, over 90 documents and decision gate deliverables produced, including 180,000 connections between elements. So the positive impact for the Mars 2020 team has been a deeper level of technical rigor. So the team completed detailed modeling and communication between systems and subsystems. And so they were capable of high fidelity connection tracking, like understanding which artifacts are connected. So the tracking of deliverables was one of the key accomplishments of the project and was enabled by OpenMBE. And we'll hear more about this in the next section, but Boeing has utilized OpenMBE at the enterprise level with over 1,000 concurrent users across 50 programs, and Lockheed has adopted OpenMBE as well with 100 concurrent users across 50 projects. So we've seen with these examples that there are a lot of users that have adopted OpenMBE within their organization. But the vision that we have is that we can take things beyond being within an organization and really make it inter-organizational. So being able to connect with OpenMBE directly between organizations. And this is the example that we're hoping to execute with the Mars sample return mission, where users will be able to connect different OpenMBE deployments and have access to all the information that is being used for different parts of the mission. And hopefully one day we'll be able to connect across essentially an entire fabric of models in cross-references. When Robert Carbon, one of the leaders of OpenMBEE, talks about this, he typically references his time at CERN in 1990 when the very first web server went online. And he compares that experience to now when he's hoping that he's experiencing the first global engineering system coming online. So I guess that's a taste of the vision that we would hope to achieve with OpenMBEE. So at this time, I'm going to pass it to Lucas, who will present about how OpenMBEE has been adopted at Boeing.
Yeah, thanks, Myra. I'm Lucas Aviles. I'm on Boeing's second century MBSE team, where we deploy a whole model-based systems engineering tool suite to the entire enterprise, including OpenMBEE. And I'm going to talk a little bit about that. Next slide. So here at Boeing, we have very large, very highly integrated systems, and we have correspondingly large, highly integrated models. This table here is something that would be typical of one of our commercial airplanes. You can see the numbers here are pretty impressive. 2,300 functions, 10,000 data flows, on the order of millions of individual data parameters being processed, model elements in the 50 million range, 10 gigabytes or more worth of data, and all of that's being touched by 1,000 modelers or more. And clearly, handling that much data is no small task, and we need to use something like OpenMBEE in order to be able to keep this much data straight and not drown in it. Next slide. So in order to do that, we deploy our systems engineering toolset that includes OpenMBEE, so we can take advantage of all of that functionality that Myra just described. This is sort of just a flowchart of how we deploy it at an enterprise level. So we have one single enterprise environment that all of our users are on. We start in the upper left with the OpenMBEE GitHub. It says JPL, but we're trying to be more inclusive. We pull that down. If there's a major changes, major versions, we'll do some initial testing in like a VM sandbox. And then when we're ready to work on it, we'll move it to a dev environment. Once we're in the dev environment, that's where we will work with the OpenMBEE code. We work on things that slot into OpenMBEE or draw from the same the MMS repository that Myra was describing. And then we also just develop other things as other part of our systems, plugins for Cameo, things like that. We run it on a scaled agile framework, so we have a large 3-month program increment split into sprints. And so each sprint we push to a test environment where we would do automated functional testing, your scalability. And once it's past that functional testing, that's where you can see that kind of feedback where we would contribute back to the open source community. And at the end of that increment, once we have tested everything and are ready to release to our internal customers, we push to a pre-prod environment where we do our final testing, system tests, user acceptance tests. And once that's complete, we push to prod on a release weekend kind of thing. And we have a disaster recovery environment that's parallel to that we do backups to in case things go wrong. Next slide. So with that process, we get a global deployment of a single large OpenMBEE powered environment across our entire organization. So we have international users across the entire Boeing company. This map here is actually even a little bit out of date as well. You can see we've got our major locations in the United States. Those other dots are for Moscow and Russia and India. We also have users in Boeing Defense UK and the United Kingdom. We have Boeing Research and Technology in Europe, users across Europe, and also Boeing Defense Australia that aren't shown there. And for those far-flung locations, we take advantage of Citrix and virtualization to reduce latency and lag for some of those users. And all this, like I said, is one large deployment of OpenMBEE. We use the Teamwork Cloud and the MMS access control system to partition the data. So we have a system set up where users, request access to specific projects on the servers, and with permission from the model owners, they can get access. So we grant that approval by project. Next slide. And so with that global deployment, we have a common tool, a common modeling language, common training, and that one big environment across the enterprise. And that means that we can collaborate really easily across the entire company, and we can be very interchangeable across the entire company. When a user needs to help out another project, or projects need to collaborate with each other, or any number of connections across our entire organization, all of that's really easy because everyone is already in the same server setup. They already have the same software deployment, and it's just a matter of getting access to whatever projects people want to collaborate on. And then with that data lake of OpenMBE and the MMS server, we can use that source of truth to connect downstream engineering artifacts, things like using our systems architecture that we developed with OpenMBE to drive network and wiring design downstream in the electrical design space, connecting to our PLM systems to model-based design. And the other benefit of having that common IT infrastructure and single deployment is that for these individual programs, they don't have to worry about that anymore. In a lot of cases, there are times when a small group wants to start up a modeling project, do a small study, especially on our defense side. You have really small groups that just kind of spin up with maybe a dozen people. And in all of those cases, those users don't have to worry about where they're going to host their models, how they're going to, what machine they're going to have to get to run everything on. They just have to create that project in our enterprise environment, and they're off to the races and ready to go. Next slide. And along the way, we've learned some lessons. One thing that we've had trouble with in the past is migrations. When we have this much data being worked with, migrating between versions of server software is no small task. We've had nasty surprises on release weekends in the past. And so now we try to test these migrations as early as we can with as much real data as we can. We try to make sure that we contribute back to the whole open source community. That way, we don't go straight too far from what the rest of the community is doing, and we can take advantage of all of the great work that everyone else is doing as well. With that, enterprise deployment, we need to have enterprise level security. Obviously, with this much data being kept on these servers, we need to make sure that we're not exposing them in any way. And so we have to do comprehensive security scans on everything that we deploy before we can bring it out to users. And that's part of an enterprise security solution as well. I mentioned before the Citrix solution that can help with latency and configuration of software. When you're working with a server that's halfway around the world, that can be difficult. And I talked about the restricted repositories and the way that we try to use Teamwork Cloud and MMS for access control. The other thing that I should mention is that we would obviously prefer it to be this way, but we are aware that one size does not fit all. We have cases where different customers might require different versions of software that is in our enterprise deployment, or cases where companies that we collaborate with or suppliers might have different deployments with different versions of software. Or even in the defense side, we have classified programs that can't be connected to the internet at all. And so in all of these cases, we have to be flexible with our deployment and make sure that our enterprise system is flexible enough to be able to support those kind of use cases as well. And with that, I will pass it back to Myra, and she can talk about the deployment at JPL.
Yeah, thanks, Lucas. So in this section, I'll discuss in more detail how we have used OpenMBEE at JPL to provide an integrated environment for systems engineering. So at JPL, I work in the CAE Systems Environment Team. It stands for Computer Aided Engineering Systems Environment Team. And really the goal of this team is to provide an end-to-end systems engineering environment for the engineers at JPL. So more specifically, we develop the capabilities of the systems engineering infrastructure, and then tailor those environments to meet the specific needs of the flight projects. And from there, the flight projects can use these systems engineering environments to complete their tasks and produce deliverables. And really the idea with this environment is that we want these flight projects to have their models be connected to the artifacts that they produce. So a lot of engineers already use models, but oftentimes they are disconnected from other project deliverables. So they may take their model, but then copy and paste or do some sort of manual transfer of the information into the documentation, and then give that documentation to the person who is responsible for implementing it in code. And then test cases are created based on the code that was written. So in this example, the connections between the deliverables are weak at best, and in some cases non-existent. And there's a lot of opportunity for error. So when we provide the systems environment, the situation that we want to have is one where the models enable consistency across the transformed artifacts. So in this example, we would find ourselves generating the documentation and the code directly from the model, or performing analysis directly on model data. And when we do this, we have greater confidence in the correctness and consistency of our information. So with the systems environment, we enable the connection between artifacts by having a multi-paradigm modeling environment that is composed of a variety of apps and services. So rather than trying to use one single tool to rule them all, we really can take advantage of the benefits of each tool and bring them all together and work on creating integrations between the apps and services that we have. So we see here a few of the apps and services that are part of our systems environment. And the key concept here is that OpenMBE is really at the center of our systems environment. So Model Management System, or MMS, is one of the data repositories that we frequently use to store our models. And View Editor is one of the most popular ways for engineers on the flight projects to consume model information. And this is particularly the case for engineers who are less familiar with modeling languages, so would prefer to look at a document in a web app. We also have several model development kits in play. For example, the Magic Draw or Cameo Systems Modeler MDK is probably one of our most commonly used MDKs for connecting SysML models to MMS. But we have several others that we use. Another popular one is kind of just the Jupyter adapter to get your model data out of MMS and into Jupyter so that you can code with Python, for example. So really, OpenMBE is kind of the core of the systems environment. And we've kind of built on top of that to really bring value to the flight projects. So with this environment that heavily relies on OpenMBE, we have the ability to support an integrated pipeline for systems engineers at JPL. So they can use our systems environment to collaborate and capture information, to do requirements and system design, then to do an analysis, and then kind of publish the results of that. And because of OpenMBE, their data remains connected throughout this entire process. So last couple of slides here to talk about the goal for OpenMBE looking ahead really is to produce large-scale engineering ecosystems. We want this because engineering really isn't performed in isolation, but rather through collaboration with other groups. So two of the elements that are part of kind of our long-term strategy for a global engineering system are, first of all, Jupyter, which brings multi-language analysis capabilities. Essentially, we want to kind of marry the popularity of programming languages like Python with the rigor and durability of systems modeling. Other key enablers moving forward are SysML v2 and other standards. And lastly, we want to enable kind of novel data-driven analysis with advanced capabilities, but more importantly, like provide these as a service. So be able to do things with OpenMBEE like graph querying or distributed computing or real-time collaboration, kind of like Google Docs. So for the last slide of this presentation, just a couple updates on OpenMBEE. OpenMBEE has a new home with NumFocus. And for those of you that don't know, NumFocus is an organization that kind of sponsors and promotes open source software. So OpenMBEE is one of those, in addition to some other notable open source projects. And of recent, OpenMBEE has been kind of getting a lot of attention and kind of gaining some popularity and has been discussed at some popular workshops such as Models 2020 and the IncQuery International Workshop. So it's definitely an exciting and engaging open source community to be a part of, and hoping that we'll continue to grow and produce great things for the systems engineering community. Any questions?
Yes, thanks a lot, Myra and Lucas, for the great presentations. Any questions from the audience? I'm sure there are. No? Otherwise, I have a couple of them. So the first question that I have is the following. So in order to manage the collaborative work among different stakeholders and different people working on the same project, essentially you decided for having an authoritative repository. So right, so all the people essentially connect to the authoritative repository, and this is the container of let's say the element that contains the model that represents everything about the project. So essentially a model that is a sum, let's say, of everything, because from that model you generate documentation, source code, all the different artifacts. Now, of course, this way of doing allow as a pro, the pros is that you avoid, you simplify the consistency management, because you don't have different views that are inconsistent, right? So essentially, by definition, the model is consistent. But as a problem that you might have is that you reduce the reusability, I guess, of the model, right? Because you don't have modules that you could reuse. And also, you might have also issues in searching for some parts of the model that you might reuse again for new projects. So can you comment on this?
Yeah, I think that's certainly a good point. To kind of build on that, we're using lots of different apps and services working on the same model data. So at times, yes, it can be kind of fairly confusing to kind of understand what changes are being made when you're looking at the model from one app or service versus the other. So I guess in terms of sort of breaking for reusability, we tend to kind of break the models into kind of separate models, but still stored within MMS, but still kind of chunked into smaller sections, so that there kind of is the opportunity for reusing those in your own project, since they're not all kind of packed into the same file. And then to kind of clear up the ambiguity that users may have for kind of understanding what changes have been made to the model from other apps or services, I think that really has kind of come down to organizing the views of the model. So particularly when we're generating the documentation, kind of having it be comprehensive, but also sort of organized and structured. Again, as I said, we really heavily use View Editor. So even if a modeler isn't necessarily, interacting with a model in View Editor, they might be using some other app and service. I would kind of really rely on the documentation in View Editor to kind of provide that overview so that everyone can see what's going on in the models.
Yeah, and from the Boeing perspective, I could add, one of the ways that we try to account for reusability with our models is that we create model starter kits that are basically the structural framework of a particular project, a commercial airplane, a particular derivative, or a certain platform on the defense side. And then also, we also use the MMS to unite federated models. Our models bump up against what is possible from a scalability perspective, even just for the off-the-shelf tools like Cameo. And so one of the things that we do is we do split our models apart in MMS, but we build querying systems that can traverse the entire MMS repository and pull data from any of the models on that repository. And that lets us kind of get the benefit of that modularity and kind of get around some of those scalability concerns while still being able to view these models as one large connected source of truth.
Yeah, thank you. Yeah, this morning we had a presentation from Antonio about Hawk, that is a tool for indexing models. And since you are talking about very, huge models, so I'm guessing if you have any indexing mechanism for even supporting the queries that Lucas, you were talking about.
Thank you for the question, David. I was going to make it.
Yeah, okay. Yeah. So if you want to do it properly, please go ahead.
Yeah, so go ahead.
You can go ahead.
No, I was just going to reiterate the question from David in terms of the searching, because I was looking quickly at the manual for, say, the view editor, and I was wondering, how do you refer to SysML elements from inside a view and things like that? You must have some way of finding them or referring to them, I guess.
Mm-hmm. Yeah, so I guess there's a couple things here. To generate the views in View Editor, we're using the docgen query language. So really with that in our model, we kind of query and choose the elements that we expose to View Editor. And that's how we create the views with that kind of viewpoint method paradigm using docgen queries. One of the other things that we use for kind of indexing and querying models is IncQuery. So we've been working more with using the IncQuery platform for running fast queries on some of our larger models.
Thank you.
Thanks. Any other question?
I have a small question. This is Felicien.
Yes, please go ahead, Felicien.
I was looking at their website and they have that view editor. So I was asking, is it possible to reuse that, and do they provide the graphical editing, or is that the way of consuming the data?
Sorry, Felicien, the voice is very low.
It's very quiet.
The volume?
Okay. Let me see. Okay. Now can you hear me? Oh, it's very low. Can you hear me now?
Yeah, maybe stay closer to the microphone.
Okay, I was referring to the view editor that they have. So is it possible to reuse that in case of diagram level? I mean, is it possible for a user to reuse that component of a view, or a developer to use that view editor component of OpenMBEE, or it's just tightly connected to the OpenMBEE ecosystem in general?
Yeah, so View Editor is a component of OpenMBEE MBEE. It kind of fits in with the model management system for kind of the repository for our models and references, and then view editor for kind of interacting and creating documents and viewing the model data, and then those model development kits for connecting different apps and services to MMS and view editor. So those are the three components. So yes, view editor is part of OpenMBE. I didn't quite catch your question about the diagram part of it.
Yeah, I guess what Felician was asking, if it is possible to reuse the view editor as a component in other projects, so without using the other parts of OpenMBE. So if you, I guess, is it correct, Felician? This is what you wanted to ask?
Yeah.
So I think the answer for you is not quite. So not quite as a standalone. So the information that you see in view editor is backed by MMS. So it's essentially taking those docgen queries of the MMS data and publishing them to view editor. So if you wanted to have like a completely different instance of view editor that was populated with the same data, you would need to have it kind of backed by MMS as well to kind of hold the data that view editor is showing. But since view editor is a web app, that means that anyone can go to that URL that has access and see what you have in your view editor page. And so I guess in terms of reusability, it's highly accessible. So other projects could look at the view editor pages of other projects. And you can even export them as PDFs and Word documents and things like that. So view editor is backed by MMS data, but it is fairly accessible by other groups once you've kind of got it, have it deployed.
Okay, thank you.
Thanks. I don't know, any other question? Otherwise, we thank the speakers. Any other question?
Just one very quick question, if
yes.
I may. Yeah, thank you very much for your presentation. I was looking at the OpenMBE website, and I was wondering if the 30-meter telescope model is available, because I can see a link to the editor, but not to the actual model.
Yes, the model itself is available. I believe it should be on the GitHub page. So if you go on the website to the participate section and then follow the link to the GitHub page, it should be in one of the repositories on that GitHub page. And yes, there also is the view editor link to it as well.
Okay, so what format is it in?
The model itself is probably in an MD-zip format. So if you have access to Cameo Systems Modeler or Magic Draw, you would be able to open it up in that tool. Yeah.
Okay, great. Thank you.
Okay, thanks a lot. Thanks again to the speaker. And I think that this was a long day. So we went through the whole program. I would like to thank all the speakers that we had today. And of course, we will have the recording of this workshop on YouTube. And yeah, thanks again all. And stay tuned with the Lowcomote project. Thanks. Thanks all. Bye.
Thank you.
Thank you.
Bye.
Thank you.
Thank you. Bye.
Bye.
Thank you.
Bye.